Good morning, all. I welcome to the today's first talk by Professor Vishwesh Vivare. So I'll give the brief introduction of the Vishwesh Vivare, sir. Dr. Vishwesh Vivare completed his Bachelor of Engineering in Electronics and Power System from Nagpur University in 1998. Completed also BA degree in Mathematics in 1999, and in 2004 he completed ME Electrical Control System from Department of Electrical Engineering, Government College of Engineering, Pune, and he has also completed the interdisciplinary program in System and Control Engineering, Indian Institute of Technology, Bombay. He completed his PhD with Professor Natarajan in 2012. Since also one of the he has a patent for an invention entitled laboratory setup for a learning fractional order control system in 2017. And since 2012 he is a faculty at the Department of Electronics Engineering, Ramrao Adhik Institute of Technology, Nerul, Navi Mumbai. His research interest includes fractional calculus, fractional order modeling and control, and hardware implementation of fractional order systems. In particularly, his research interest is fractional calculus and fractional differential equations like this. Today, I welcome Professor Vishwesh Vivare to start his lecture. He will talk on the FPGA implementation of special mathematical functions used in fractional calculus. So, welcome Professor Vishwesh Vivare for today's first talk. So, over to Professor Vivare, sir.
Thank you, Dr. Kendre, sir. First of all, I would like to, am I audible?
Yes, sir.
First of all, I would like to thank the Department of Mathematics and Statistics, University of Hyderabad, for conducting a conference on fractional calculus and applications, especially to Dr. Sachin Bhalekar, my colleague. I am also thankful to the organizers of the conference, and I am actually overwhelmed to see eminent scientist and mathematician Professor Varsha Getji madam, who has been my guide and mentor also, even though she didn't practically guide me, but I have learned a lot of things from her. Thank you, madam, for gracing the occasion.
It's my pleasure.
Yeah. Thank you,
My
ma'am.
pleasure.
Yeah.
I'm also very overwhelmed to see the old group and conference dedicated to fractional. So now the legacy is carried over to the new generation.
Yes. We will try our best, madam. We don't know whether we will reach to your height or not, but we'll try our best to carry forward this talk.
I'm not that great.
Anyway, thank you, ma'am. So I'll start with my talk. I'll shut down my camera so that there will be no issue of bandwidth. Share my screen. Is my screen visible?
Yes, sir.
Yeah, okay. So what I'm going to talk today is about hardware implementation of some special mathematical functions which are used in fractional calculus. There is a typo in the title slide. My apologies for that, and that too in the word fractional. So I'm very sorry for that. But anyway, I'll move ahead. What I'm going to present here is the hardware implementation of some mathematical functions that are very frequently used in fractional calculus, whether you are solving a fractional differential equation or you are calculating the fractional derivative, maybe say using simple successive differentiation formula, which is nothing but a Riemann-Liouville special case of power law type functions. You find the fractional derivative of t to the power alpha or t to the power mu. Actually, this problem we undertook 1 or 2 years ago, And what we realized while working in fractional calculus or in the areas applications related to fractional calculus, we found out that fine, the theory is very well developed and there are a lot of good results available, very strong results available. But whenever it comes to acceptance of fractional calculus or fractional calculus applications in by academia, or you can say more specifically industry, okay, so at that time we realized that if you can provide them with some good ready kind of hardware setups which can implement uh, let's say fractional derivatives or special functions on any hardware platform, then the industry acceptance would be more for fractional calculus as a field, because in theory or in simulation you get very nice results. You can show that if we talk about fractional order control, then if we talk about that, we can show by derivations or in theory analytical methods, also with simulations, that the fractional order control is much better, much tighter, more reliable, more robust as compared to integer order control, where you use simple integer order derivatives. But the everything boils down to the situation or the question: how do you put it on a microcontroller? How do you put it on an FPGA? How do you put it on a DSP processor? Because the industry wants that. So our group at Department of Electronics Engineering, RAIT, we carried out dedicated work, in very focused work in this, and these are some of the results that I am presenting to you. Actually, we have got an Australian innovation patent granted on the work that I am presenting. It was granted a couple of months ago, and I thought that I will put it in front of all the experts and fractional calculus enthusiasts, so that we can see and we can get the feedback also. So what we have done here is we have not gone with the conventional way of approximating a fractional order system, or let's talk about the special functions. Let's take a gamma function. Now if you see the gamma function, it has got an integral representation, it has got a series representation also, it should be available, okay. But implementing that on a hardware which has got a limited memory, which has got limited resources in terms of in terms of power consumption and all those things, it becomes very difficult. Next example is the Mittag-Leffler function. Now we know that Mittag-Leffler function is the backbone of fractional calculus. In fact, it is an eigenfunction of the fractional differential problem. Okay. Now, if you try to implement a Mittag-Leffler function on a hardware, okay, and if you look at the available literature, you will find out that there is an algorithm which is, there is a series definition of Mittag-Leffler function, but then the issue is your summation k goes from 0 to infinity. Now, what infinity you will consider in the as an upper sum? What number you will consider? How much terms you will be allowing in the Mittag-Leffler function expansion? Now, if you keep, say, n is equal to 10 or n is equal to 20, then the approximation that you get for a Mittag-Leffler function is not that accurate, and there are some deviations in the results. Second way is, there is an algorithm, there is a paper by Gorenflo et al., and I think Professor Igor Podlubny has developed a very nice MATLAB routine for that, which is known as MLF, that function. And if you use that in MATLAB, it immediately gives you a very nice and accurate value of Mittag-Leffler function up to the accuracy that you desire. But again, implementing it on a hardware platform would be very difficult, because then you would have to solve those I think he has used very complex mathematics in that. I don't remember right now, but the algorithm that he has presented, or he has used, or Professor Gorenflo has given, actually, it is very difficult. It was we tried also that, but we found out it to be quite difficult to implement it. Then suddenly one day we were discussing, and we found out that this artificial neural networks, which are nonlinear in nature, and which gives the output between +1 and -1 only. So there is no issue of any saturation, and at the same time there is the artificial neural networks have the ability of learning, interpolating. Okay, so can we use these features of artificial neural network to model or approximate a special function and then dump it on a hardware platform? And we found out, as you will also see as the presentation progresses, that it will be we have been quite successful in doing this, and we have got really good results. So I'll proceed with this. So this is the background that I would like to this is the context I would like to set before we go into this. Okay, so I don't think on the day 2 in the international conference on fractional calculus I need to talk about things. Okay, so only the last point that I would like to say is, nowadays there is an increasing interest in the simulation and practical hardware implementation of the FO systems and controllers, and it's very so these are the standard definitions. You will Runwald, Letnico, and Caputo. Okay, let's come to the special functions. So first one is the gamma function. You can see equation 4, which is the integral representation. Now immediately below that we have put up this formula for calculating the fractional order derivative of t to the power m. Okay, and here you see you require this gamma function. Okay, that of course gamma function is also required in these successive integration definitions also. So even in the GL definition also it is required. So gamma function is a, you can say, a very critical step in required in to be calculated in order to go into fractional calculus and use fractional calculus in practical applications. Okay, then the error and the complementary error function. Now you see this error function and this complementary error function. Now if you ask me to implement this error function or a complementary error function on a hardware platform, okay, now MATLAB has got standard commands available. Okay, and it uses some numerical methods to calculate it. But if you go to industry and if you show them that, okay, this is what the algorithm is, it involves say 25 steps, and you need to code it and you need to put it on a hardware platform, and then you will get good results. They are not ready to accept that. They say that give me a method which is very easy, which I can implement it very easily with less efforts on my hardware platform, and then I can deploy it in the industry as and when required. Okay, then you can see here this error function and the complementary error function, how they are coming up in fractional calculus. So you have a fractional order differential equation, okay, which is an homogeneous differential equation, and there are the derivatives are considered in the Caputo sense. So you can use integer order initial conditions, physical initial conditions, y0 and y prime of 0 at 0. Okay, and if you take the Laplace transform, you get this particular thing, and if you solve it, you get the solution in terms of error function. Now the question is, if if I come across such type of fractional differential equation, and I know that for some initial conditions, non-zero initial conditions, this is the solution. Okay, I need to find out y of t. To actually generate y of t on a hardware, I need to implement this ERF function of under root t. If I can do this, okay, I have solved this particular differential equation. Okay, but look at the definitions that are available. Of course, I don't say that there are no numerical methods available. As I said, they are already available, but we somehow found them to be quite difficult to implement on a hardware platform. Then the Dawson's function, okay. Sorry, these are the formulae for the Dawson functions, okay. Then the BOSS, Mittag-Leffler function, okay, 1 parameter and 2 parameter Mittag-Leffler function, and you can see the conventional summation formulae are very difficult to implement. And as an example, I mean, how does Mittag-Leffler function? So you can see this is a eigenvalue problem basically, okay, fraction order eigenvalue problem, and you have a non-zero initial condition, and this is what the solution is. Okay, so if I want to solve this differential equation, I have to use a numerical method, okay, that is point number one, or I can go for the other methods which Professor Gedji and her group has come up with, Adomian decomposition method and all that. But somehow, since they are not as such numerical methods, we couldn't implement them on. Rather, we have not tried implementing Adomian decomposition method and all its offshoots on any hardware platform. Okay, so we have implemented using this ANN approach. Okay. Then this hypergeometric function, so GHF. So this is the formula. So if you ask me the practical, or you can say the involvement of hypergeometric function in fractional calculus, okay. If you look at the fractional order model of point reactor kinetics model for a nuclear reactor, okay, this comes into picture, and finally the answer comes out in this way. So you can see the reactivity. Okay, I'll not go into the details of physics of nuclear reactor, but you will find that if you solve that inverse, I have got some hardware results also based on that. So you have to, the final expression, analytical solution comes up with like this, and it involves this hypergeometric function. Okay. Now let me come to the artificial neural network. Okay. So it's a buzzword now, artificial neural networks, and the things and the areas, domains that have arisen because of that, machine learning and artificial intelligence and all those things. Okay, right. So mathematical model of a neuron, artificial neuron, is based on our biological neuron. Basically, if you see, this is the simplest structure. So you have got the structure is very simple. There is no mathematics involved in that, rather than just product of sums and all those things. Simple product and sum. That is the only mathematics involved in an artificial neural network, and that is the plus point. That is the plus point. So this is basically the structure of a neuron. So you have got a neuron has got some n number of inputs, which are multiplied with these weights W1 to Wn. Okay, and then you add them. Okay, and finally you pass this sum through a bias through an activation function. Okay, just to smoothen the output, and it gives you the output. So mathematically, these operations are very simple. So this output OJ is nothing but f in function of net j. Okay, and this function of net j is nothing but this net j is nothing but, which is coming here, is nothing but the transpose of the vector weights multiplied by the inputs. Okay, so this is a very simple operation. This is the classical McCulloch-Pitts neuron model. Okay, now you can club these neurons in cascade, and you can have a multi-layer neuron model. So here you can see what I am showing here on the left is there is a set of neurons, okay, and which are connected in a particular fashion, and you get something called as a multi-layer neuron model. And the mathematics becomes slightly complicated. In place of arrays, you get matrices of weights. So these are the matrix weights for the first layer, this is for the second layer, and this is for the nth layer. Okay, now you have to make a neuron to learn, or a multi-layer neuron network. You have to make it learn. Okay, so there is a simple optimization involved in this. So so what you do basically, you feed the neurons with a set of inputs, known inputs and known outputs, and you carry out iterative process, and you also minimize some criteria which might be like the error between the actual output and the output of the neuron. So you make these neurons learn. In other way, you just fiddle with this set of this matrix of weights. Sorry, you fiddle with this matrix of weights, and you finally come up with a set of weights where the error between this actual outputs and neuron output, it becomes less than some threshold, okay, which you decide. So this is what is this algorithm. Okay, this is known as a Levenberg-Marquardt algorithm. So we have done all this in MATLAB. This has been implemented in MATLAB. In fact, MATLAB has, those who have been using MATLAB, they will know that MATLAB has got a dedicated tool for implementing neural networks, which is known as NN tool. That is available. Okay, right. Next, I come to the hardware platform that we have used. So we had a choice of microcontrollers, field programmable gate arrays or FPGAs, and we also had something called as DSP processors, and we have implemented on all the platforms. Okay, but the results that I'm presenting here are on the FPGAs. So as you can read the text, that they are reconfigurable semiconductor devices that consist of configurable logic blocks. So basically, you can configure the logic blocks which are available in the in an FPGA, and in order to reconfigure or configure those blocks, you have to use something called as HDL, which is known as hardware descriptive language. Okay, so FPGAs basically come under something called as GPUs. Okay, the advantage of using FPGAs over other hardware platforms like microcontrollers and DSP processors is that since you are working at the basic reconfigurability of the logic blocks which are present, memory blocks which are present there, okay, the speed of operation of FPGAs is fast as compared to the microcontrollers and DSP processors. Of course, every hardware platform has got its own domain of operation. Okay, but FPGAs are now have been accepted worldwide and by the industry as well as the academia as the fast operating blocks and the fast operating hardware platform. Okay, most important thing is the power dissipation, because when you come to implementation and when you come to power conservation, even a even a factor of milliwatts also matters a lot. Okay, so it has been proved in literature and experimentally that FPGAs dissipate less power, okay, as compared to their counterparts. Okay, and the last point is very important, that FPGAs do not have to fetch and decode cycle, hence competition time is less That's what I was saying. They are fast as compared to the other softwares which are other hardware platforms which are available. Okay, right. So I have already explained this slide motivation. Okay, so we wanted to implement the special functions using ANN. Okay, and on hardware platform. Fine. So this slide basically explains what is our workflow. So we create and train neural network which will approximate the mathematical function with minimum error. So you take a function, let's say a Mittag-Leffler function, you find out you simulate the Mittag-Leffler function in MATLAB using maybe Professor Podlubny's algorithm or any other algorithm. You get the input-output for the Mittag-Leffler function. You store that data. Then you use MATLAB neural network toolbox to train your ANN. You appropriately choose the layers and the algorithm also. And after that, once you have trained your ANN offline, it's not a real time, offline. Okay, you carry out iterations and you come up with the best ANN which will minimize the output of the ANN and the actual output or the actual time evolution of the Mittag-Leffler function. I'm just giving one example. Okay, once you do that, the ANN that you have now, which is trained, is nothing but your Mittag-Leffler function. Now, what remains is just implement that ANN on an FPGA platform, and it works very well. Okay, so that is what I have explained, step number 1 and 2. Okay, then you do some kind of fiddling to reduce the computational time with ANN. Maybe you reduce one layer or something like that. Okay, and then the fourth step is you implement that FPGA on FPGA of ANN network and study the resource utilization of these functions on hardware. And then the last thing is represent various applications of mathematical functions. So this is what we have done. So these are some of the contributions. I think I'll come to them later. Okay, so this is the simple network that we have used. We have used a laptop to train the neural networks, which has a MATLAB and a sufficiently good, you can say, configuration. Then once the ANN is trained, it is dumped on an FPGA. Okay, and then the FPGAs are implemented in real time. Very simple. It doesn't require very big experimental setup or something like that. It's very tabletop thing. Okay, this is the Altera board, FPGA board that we have used in carrying out this study. Okay, so these are some of the details of the FPGA board that we have used. It is a Cyclone 4 series, and it has these many logic elements, and this is the memory specification of this. It works at 50 megahertz clock. Okay, and it has got 18 slide switches and all these peripherals, LEDs and all those things. Okay, connectors. So these are the connectors. I'll just skip this. Okay, so this is how we have done. So you acquire the input and you train the ANN, then to design the ANN using VHDL, then you synthesize it, then you generate a bit of stream file. Okay, you put it here, and finally you come up with the implementation. Okay, so this is just, I have shown one layer. Okay, so you see how this is happening. This is how it is happening. The ANN is being implemented, okay, on FPGA, and this is how it takes place for a particular ANN. So particular one layer of ANN, it has been zoomed here, and this is how it is being implemented here. Okay, so this is the RTL view of the ANN implementation of the function. Okay, right. Just give me a moment, just a moment. Yeah. So you can see this is the RTL view of the ANN implementation, and everything is done using MATLAB. Okay. So you don't have to do the VHDL coding and all those things. Okay. Because the industry is not ready to do the coding and all those things. Okay. They do have expertise, but they just want something with a click of a button. So you see here in all this complete exercise, what we have done is we have used a mathematical computational software called MATLAB to train the ANN and use the same MATLAB to dump everything on FPGA. Okay, so my team didn't sit with doing the VHDL coding and all those things. They just use this the tool, the module of Simulink, which is available, and they implemented it on the FPGA. Okay, right. Now this table will make a sense when we actually see the results. I'll come to this later. Okay, right. So okay, fine. So first thing is comparison between simulation plot and MATLAB plot. So you can see this is the gamma function, and this is the error function. So the plot above, let's talk about the gamma function, shows the actual implementation of MATLAB along with its ANN. Okay, and you can see how closely the curves are matching, and the bottom one is the error. So you can see the error is almost zero. Second one is the gamma function. So I have not shown you the result up till now on the DSO. Okay, I have not shown you the results on digital oscilloscope where you can see the actual implementation. These are just the simulation results that I am presenting. Next is the error function. Okay, again you can see. Then the complementary error function. Then the Dawson function, which has been implemented. Okay. Next is the Gauss hypergeometric function, and the last one is the Mittag-Leffler function. Okay, so these are all simulation results. So things look very nice here. Okay, so what these results are, you have a Gauss hypergeometric function. You use MATLAB code to execute it. Then you train an ANN and you compare the output of ANN with the actual hypergeometric functions output, and you see that they are matching. So the ANNs are ready now. They have been well trained, and they can be deployed on an FPGA board. Okay, right. Gamma function, error function. Right. Fine. Now let's come to the real-time implementation. Now here you see the gamma function. Now what you see here is a digital storage oscilloscope DSO output. Okay, and it has been implemented on an FPGA. The ANN approximation of the gamma function is implemented on an FPGA, and you can see the result in the on an oscilloscope in the laboratory. Okay, next is the error function. Okay, next is the complementary error function, the Dawson function. Okay, of course you will not get the smooth results as you saw in the simulation. Okay, here when you implement it on hardware, there are a lot of factors which are involved. There is some noise which is there in your cables and all those things. So, okay, so you don't get a very smooth and nice looking output on in the hardware implementation, but this can be removed. I mean, it's not a big problem. Okay, right? But you can see now, look at this Dawson function. Now, if you wanted to implement a Dawson function on an FPGA, you need to actually take some numerical method available in the literature, which may involve some numerical integration or whatever it is. Okay, and then you have to code it and you have to implement it. And the most important issue that we found out, okay, especially while implementing these special functions and fractional calculus definitions and all those things, we found out that our hardware immediately reached to saturation. Okay, because the output went to infinity or output went to a very large value, and if you try to implement a fractional order derivative, okay, it has got a singular kernel, weakly singular kernel, so at some point of time it is going to blow out and your hardware is going to go into saturation. So all that can be avoided if you go for the ANN approximation, and once you do that, the things becomes very easy for implementation. Then this is Gauss's hypergeometric function, and the last one is the Mittag-Leffler function that we have implemented. Okay, now you see the root mean square error. The question that arises is, okay, you have done all these implementations, but what is the guarantee that whatever output you have got or the functions that you have implemented, whether they are correct or not? Just getting implemented them is not enough. You have to implement them as accurately as possible. Okay, that is very important thing. So this table speaks for that. Okay, so gamma function. So what we have calculated is the root mean square error. Okay, so for the gamma function, while doing the training means you have the actual gamma function input output, then you have the ANN, okay, and then you find out the minimum error. Okay, you compare the outputs of the trained ANN and this. Okay, you found out to be 9.8 into 10 to the power minus 4, which is very less. Okay, and when you simulated it, you simulated the ANN and you got the actual function and you compared their output. The error is 2.57 into 10 to the power minus 2, and when you implemented it on hardware, you got it sorry, 2.46 into 10 to the power minus 2. So you see the implementation of ANN or the ANN approximation of the function on hardware. Okay, it has still preserved your accuracy, and you can see that the implementation has been quite accurate. Okay, an error of 10 to the power minus 2 or minus 3, I don't think, and that too is a root mean square error. Okay, it is not a big error. Okay, and you have successfully implemented it on an FPGA platform. Okay, next we didn't stop up to this point. What we did is that we actually use this ANN, okay, ANN approximation to calculate the fractional order derivative. Okay, so 0.5th order derivative of t square, we know that this will have a term called t to the power 1.5 with some coefficient, which is gamma, mu plus alpha, and all those formula. Okay, so this is the simulation result, and this is the hardware result. Now what I am trying to tell here is that now I have an ANN which has approximated or which is mimicking your gamma function, and since you have got an ANN which has got a learning capability, you can train a single neural network for different values of alpha for gamma function. Okay, like I can train a single neural network for gamma from 0.1 to 0.9. I can have a single neural network which can be replaced for any gamma of 0.1 to 0.9, not only the 0.1, 0.2, those steps values. If you train it properly, you give any value of the argument. Let's say you want to find gamma 0.65. Okay, now gamma 0.65 can also be implemented using the same neural network which you have trained. While training, you have to do it more rigorously. It is more time consuming, but as you know, as I said, training is offline. ANN training is offline. You do it. Okay, once you are done with that, Okay, now you are ready with that single neural network, okay, which can mimic or which can approximate any gamma value or gamma of any value between 0.1 to 0.9. I mean, you choose that range. Okay. Now that can be used to calculate the fractional derivative using this formula. Even you can also use it to find out the fractional derivative using the successive integration formula also. We have done it for a simple thing, but it works. In fact, in the last conference on fractional calculus conducted by Professor Geji Madam, we had presented some results where fractional derivatives in all three definitions, Caputo, Riemann-Liouville, and Grunwald-Letnico. We tried this, and any value of fractional derivative between 0.1 to 0.9, okay, you train your neural network. Now you just forget about what value of alpha it is being sent to your neural network. Your neural network is going to spit out the near accurate value of fractional derivative of that function. You see, that's the amazing thing. Okay, now Dawson function is involved in the solution of this differential equation. Now what we did is the ANN that we had developed for Dawson function, we plugged into that. Okay, now I hope you will understand what I'm trying to tell you. The analytical solution of this differential equation involved a Dawson function. Now in that analytical solution expression, we removed that Dawson function and we plugged in our ANN there, and still you get the right result. Okay, so the ANNs are working nice in standalone. Also, they are working nice in combination with some other mathematical functions. Okay, and that is working perfectly. Okay, then nuclear reactor model. Okay, this is how you get the result for that. So inverse point reactor kinetics model. Okay, and you get this result. I don't know whether the hardware result is available. I think they have missed it. Okay, so I am presenting the table for the hardware implementation of inverse FPRK model. So if you can, I'll just go back slightly and I will show you. So this is the hypergeometric function, okay, which is multiplied with this e to the power minus kappa t square into t to the power 2 minus alpha multiplied by 2 into capital lambda into kappa divided by gamma of 3 minus alpha, okay, plus beta. This gives me, for some set of values, this gives me the reactivity. Okay, now what result I am going to present to you is that where this function has been implemented with ANN, this gamma has been implemented with an ANN, and I have found out the row complete, and it matches with this hardware implementation of inverse FPRK model. So you see, for different values of alpha, okay, you get the same result which the theory is giving you with the ANN approximation. Okay, right, and you see the logic elements that are consumed. Minimum resources are consumed. 19% of total logic elements. Total memory registers that have been consumed are 5374. Total pins that are used are 13%. Okay, total memory bits are 3%, and embedded multiplier 9-bit elements are 25%. Okay, Divya madam, do we have any power consumption here? I have my colleague Ms. Divya Shah, who was instrumental in implementing all this in FPGA.
Yes, sir. Actually, I didn't put it here, but our power consumption table is in the previous slides for one layer of neuron.
Okay, let me check.
Yes.
This
Here,
one?
yes, sir.
Yeah.
Yes, sir.
Okay.
This
So
is
can
for
you
one layer of
can you
neuron.
please chip in and tell about this particular thing?
This is basically the power consumption of the NN implementation of a function where we use the one layer of the neural network, in which 10 neurons are uh, basically trained. So this power dissipation and the frequency analysis is based on the software we have used. Okay, whatever code we have written for the particular implementation of the function, and based on that, the synthesization software will give this operating frequency estimation and the thermal power and static thermal power dissipation, while we will implement it on the hardware. So it is basically before we do the hardware implementation, the software will give this particular results.
So they are just the predictions by the software.
Yes, sir.
Okay. Right. So you can see, we can say that the power consumption is very less here in this case.
Yes, sir. Yes, sir. Using ANN.
Wow.
So using ANN, we can see like if we have implemented before without ANN approximation, right? So at the time, like power consumption and the frequency was very, very high.
Okay. So that it would have been nice if we had put that also as a one more column here. Anyway,
Yes.
but this is what is so in a nutshell, if I would like to conclude it, okay. So these special mathematical functions like gamma, error, Dawson, GHF, and ML functions are computed using neural network, and we have implemented it, okay, on FPGA. They are ANN approximations, okay. Right. So the last 2 points are very important. ANN is an easy way for implementation of complex functions. Using ANN for implementation and a less number of logic utilization. So overall, the resources consumption is very less if we use this ANN approximation, and these results are really very good. Yeah, fine. So we come to the end. Questions are welcome.
So now the session is open for a discussion, please.
Can I ask something?
Yes, sir.
You know, finding zeros of Mittag-Leffler function is something which is quite important. And in my lecture yesterday, I mentioned that when you want to study zeros of Mittag-Leffler function, which is related to the intersection of trajectories and things like that. So can this ANN, it is also very tedious job to find zeros of Mittag-Leffler function. And Professor Gorenflo, Luchko and their group, they have developed programs for that. So I was just curious if ANN can ANN be used for such purposes?
I will have to check that, madam. I can't answer
Okay.
extemporally for this, but can be worth explored.
So for implementation of ANN, you should know the end result and then you optimize.
Exactly, that is the thing. That
So
is the
I
only
think
point. That is the only point, because you need to train an ANN.
okay.
I mean, training requires the known correct input-output data. Input-output in the context of a neural network, because you have inputs, you have outputs. So you need to know the input-output, for which input you get the right output, and then that is to be used to train a neural network.
Okay. Okay. But still, it is worth exploring this ANN.
Yeah. In fact, our results are such that now we are planning to move ahead, and in fact, more complicated fractional order systems we are planning to implement on using this ANN, because the most important problem that we face is, okay, you give me Caputo fractional derivative or a differential equation or a system which is modeled by a Caputo differential equation, fractional derivative differential equation. Now, fine, it's okay. I mean, you get an analytical solution, you have got a numerical solution also available for that. But if it is a part of some hardware bench which is required to be implemented, then how do I do it? Then it becomes very difficult. The advantage that we found out, or rather we have tried to exploit about ANN, is that the learning capability or the interpolating capability of the ANN has been used.
Okay.
Now, our next target is to train an ANN for modeling fractional derivative for a set of functions. I mean, we have basic functions which are required in engineering, which is basically a exponentially increasing, exponential decay, sinusoidal, shifted sinusoidal, co-sinusoidal, impulse, ramp, step, and all those things. Now, we are planning to design a single neural network which will be a fractional derivative of for any of these functions which are input, of course, in a range with any fractional derivative order. Now, if that works, then it is a standalone neural network which you can say that, okay, do you have a sinusoidal function for which you want to find the Caputo fractional derivative of order 1.3? Okay, just use this. This is going to work. Like that. So that is what we are planning to do. Because industry has got this major objection that, okay, fine, it works very nice with PID controller, fractional PID controller. You are showing that your system has become more closed loop robust. Its stability has increased. Fine, you are rejecting the disturbance. Everything is fine. That's okay. Tell me how to implement it. The moment you talk about implementation in the conventional fractional order control, you have to go for Austerloop's recursive approximation, aura they call it, which has got a limited memory approximation. So you have to come to frequency domain, you have to approximate it, and then you get a set of cascaded filters which are implementing those that fractional derivative. That too in the particular frequency band. So we also tried with that, but then there are issues involved with that. You get very high coefficients, 10 to the power 17, 10 to the power 18, like that. Then if you put it on a hardware, suddenly it saturates.
But has some industry used your this?
No.
Not yet.
So we went one step ahead. We got an Australian innovation patent filed and granted on this particular thing. So we hope that we are also in the process of going for an Indian patent for this. Let's hope when we showcase it as a tabletop thing, then I think industry would be.
So they should actually implement it on a hardware and use that hardware as a part of some machine or something.
Yeah. Maybe we will have to develop a laboratory prototype where you can show that a complex process is being implemented with this and the results are good. Because if you show them 5% or 10% less consumption of resources and energy, industry is ready to take that. But they don't want something which is very complicated. Okay, you do that and then you show that. I don't think the industries will ever be ready to accept such things. Because in control we say that we have come up with so many hi-fi controls. Okay, but industry still relies on PID control, simple proportional integral derivative, simple PID control. So that paradigm shift to occur and to make them convince would be a Herculean task. Let's hope it works out.
All the best.
Yes. Thank you, ma'am.
So next question, please. Hello.
I don't see any questions in messages.
Chat box, there is no question, sir. Yes.
Yeah.
Participant, if there is a question, please come up.
Professor Vishwesh, can you tell more about your recent patent?
Yeah, thank you so much. Actually, we had filed a patent in 2017 on laboratory setup for implementing fractional order systems. So our group here has developed a, you can say, a laboratory prototype, okay, which can emulate any type of fractional order system, okay. And where you have a laboratory, I mean, how can I show? Fine. I mean, this is the laboratory tabletop. Okay. Now this will contain, it will have all peripherals, input, output, something. Okay. And you can implement it any fractional order system into that. So it can be used as a controller. It can be used as a fractional order system and cascade of these things. So we had got this idea and we developed some the preliminary hardware for that. The patent was filed in 2017 February. It went for examination, and they gave us a first examination report sometimes in the June last year, 2021, and then we filed a reply for that. Then they had a hearing. You will not believe. I had an online meeting with the patent examiner from Calcutta Patent Office, and it was a 1 hour discussion where that examiner and tried to understand each and every part of the aspect, and I had to teach him fractional also to some level. So, but it worked out finally.
So, if given fractional order system of differential equations,
yeah,
can you provide electronic circuit or something?
Yes. It is a reconfigurable.
Yeah, because I mean, we are solving systems using numerical methods, and we are taking some step size. Okay, so there will be certain error in numerical method, and if we consider chaotic systems, then such systems are very sensitive to such errors. Okay, so we don't know whether the chaos we are getting is real or not.
Okay.
So if you can have such electronic circuits,
yeah,
or something related,
yeah,
then one can realize that it is really a chaos.
Exactly.
Okay, so
Yeah. I mean, we can of course do that, but just I would like to add to your point that Divya and I and my team, we have co-authored a paper where the title of the paper is FPGA Implementation of Fractional Order Chaotic Systems.
Yeah, please share.
Yeah, it is. So it is Elsevier, I think AEU, Journal of Electronics. It has been published, and now it is being cited because people find it very interesting to implement fractional order chaotic systems on FPGA platforms. Okay, but there at that time we didn't go for any ANN or anything. We just used the digital, the discrete versions of fractional derivatives, and we implemented it.
Actually, Geximam and I was looking for such circuit implementation of our system. There is
we can be, of course.
So
We are ready to.
please
we are ready. We can think offline, and we can have a collaboration.
Yeah,
in the future.
Thank you.
I have to also work out on one interesting algorithm. I think Geji madam and her student, I think Dr. Aman Jhinga, they have come up with very Adamian decomposition method working for a very small values of alpha, right, madam?
No, yeah, then we have another still betterment with another student, Manoj Kumar.
Okay.
And there we have a family of 6 methods actually.
Okay.
Where we have still better. I mean, like your alpha can be even 0.001.
Great.
And it doesn't blow, and it has more accuracy, and that was
Yes.
our recent work.
Yeah.
So now we have fantastically working algorithms.
Great.
So don't bother about now accuracy. They are stable, accurate, and work for any value of alpha.
Right.
So actually, this is the beauty of this interaction, that
Yeah.
this was the problem you told me in one of the conferences,
Yes,
that the methods blow for small values of alpha.
In my
So-
work, madam, I had to literally stop the simulations for alpha equal to 0.3 or even 0.4 also, because with Caputo,
so that time itself, I mean, and it is the way engineering contributes to mathematics.
Yeah.
Like I got motivated, and now our methods work for alpha point not one also. So
Yeah.
I can I will share that paper.
You have
with
shared the paper with
I think
me.
I have shared with you.
The
So
laziness
that is
on my part. The laziness is on my part. I couldn't revert to you.
One's priorities to do.
No, I will. We will in fact get in touch with you and Professor Bhalekar also.
So we will, if you just optimize, take this end product generated by these methods and then optimize, then you will get fantastic results.
I think there is no question from participants. So we thank Professor Vishwesh Vivare sir for such a wonderful lecture on fractional order control system for simulation, in explaining the term simulation, artificial neural network for special functions, and special functions involved in the fractional calculus, as well as the hardware implementation of the fractional order system. Thank you, Vivare sir, for such a wonderful lecture.
Thank you, sir. Thank you, Professor Kendre sir, Professor Sachin, and Professor Geji madam, and all the officials from the Department of Mathematics, University of Hyderabad. Let's keep the fractional order community live and thriving with new results. Thank you so much.
So over to Sachin sir.
Thank you, Vivare sir, for nice remarks. Thank you, Dr. Subhash Kendre, for sharing this session. Now, next talk is by Professor Shantanu Sahare from National Institute of Technology, Rourkela. I invite Dr. Dilip Kumar from University of Kerala to share this session.
Good morning, Sachin sir.
Good morning, sir.
Good morning, Varsha ma'am. So first of all, let me thank the organizers for giving me an opportunity to chair a session in the International Conference on Fractional Calculus. And today we have Professor Shantanu Sahare for chairing this session. And so before I invite him for his lecture, let me give a brief idea about him. Professor Sahare is currently a professor and head of the Department of Mathematics of National Institute of Technology. He has completed his PhD from Jadavpur University in the year 2008, and he received the MCA degree, Master of Computer Applications degree in 2001 from Indian Institute of Engineering, Science and Technology, Shibpur, India, and earlier he completed his Masters from Calcutta University in the year 1998. Professor Sahare is enlisted in the world's top 2% scientist list recently released by the Stanford University, and he is in number one position in numerical and computational methods area from India, and in world ranking he is at 136th position. And Professor Ray has 20 years of teaching experience in undergraduate and postgraduate level, and 19 years of research experience in various fields of applied mathematics. He has more than 210 publications to his credit, where 178 are in SCI journals, and also he was awarded the IOP's top cited author award in the year 2018 in the field of physics. And he has written a couple of books also. He has written a book on graph theory with algorithms and its applications with Springer, Another book, Fractional Calculus with Applications for Nuclear Reactor Dynamics, which is with Taylor and Francis group. Wavelet methods for solving partial differential equations and fractional differential equations, which again with Taylor and Francis group. And also he has written one book on nonlinear differential equations in physics by explaining their nature. So I think we are fortunate to have him for his lecture. So on behalf of the university as well as on behalf of the participants, I invite him to deliver his talk on analytical and numerical methods in modeling reached fractional reaction diffusion mechanics systems and reached fractional nonlinear Schrodinger equation in quantum mechanics. Professor Ray.
Thank you, Professor Dilip Kumar, for introducing me nicely. First of all, I would like to thank Professor Sachin Bhalekar for inviting me in such a wonderful conference. And it is my immense pleasure to attend this international conference. I would like to thank the organizing committee of University of Hyderabad to organize such a wonderful event. I welcome everybody for attending my presentation. So let me share my slide. Is it visible to all?
Yeah, it is visible, sir. It is visible.
Okay. So the title of my presentation is Analytical and Numerical Methods in Modeling Reached Fractional Reaction Diffusion Mechanics System and Reached Fractional Nonlinear Schrodinger Equation in Quantum Mechanics. Actually, I will give the presentation on two models. One is the Reached Fractional Reaction Diffusion Equation, another is Reached Fractional Nonlinear Schrodinger Equation. This is the outline of my talk. First, I'd like to introduce briefly the reached fractional derivative and fractional calculus. And then I want to briefly introduce the analytical method, optimal homotopy asymptotic method. And then I want to briefly introduce the second order implicit finite difference method. This is a numerical method for solving the reached fractional differential equation. Here, the first model is reached fractional reaction diffusion equation, and also this method, the numerical method, has been implemented for solving reached fractional nonlinear Schrodinger equation. And to for the purpose of comparison, so analytical method, that is modified optimal homotopy asymptotic method with a Fourier transform, has been implemented for the solution of reached fractional nonlinear Schrodinger equation. So first of all, I'd like to introduce briefly the reached fractional derivative and fractional calculus in modeling of anomalous transport phenomena and in complex phenomena. Differential equation plays reached fractional differential equation plays a significant role, and reached fractional derivative plays an important role in differential dynamical system. And in recent years, it has been seen that the fractional diffusion equation has been evolved in several fields, such as engineering, physics, chemistry, and various fields of science. And the diffusion equation of fractional order plays a significant role in modeling anomalous diffusion and subdiffusion. The reached fractional derivative is a combination of Riemann left derivative as well as Riemann right derivative, which describe the modeling of flow pattern impact both sides of the domain. So the diffusion equation of fractional order plays a significant role in modeling the anomalous diffusion and subdiffusion that I already explained, and also explanation of random walk of fractional order and wave propagation phenomena, and many other phenomena. In the field of physics, spatial derivative with fractional order is being utilized for modeling anomalous diffusion in which a particle advances at a rate which is not consistent with classical model of Brownian motion. So reaction diffusion equation emerges naturally in the system, which consists of several interacting components and used to explain the phenomena relating the pattern formation in various fields of chemistry, physics, and biological systems. Let us consider first the reached fractional reaction diffusion equation given by equation 1 with the initial condition uxg equal to phi x given by equation 2 The domain of this Rich fractional reaction diffusion equation is AB, and Dirichlet's boundary condition is given by equation 3, that is UAT equal to UBT equal to 0. The Rich fractional derivative has a dual and non-local nature, for which it becomes very essential to be utilized in the fractional modeling, that is diffusion equation. So to solve such an equation, Rich fractional reaction diffusion equation, we required an efficient technique and a sophisticated technique, because usual classical method cannot be applied for solving such an equation. So an impeccable and efficient technique is essential for this purpose of solving Rich fractional differential equation. So in the year 2006 and 2007, Chen and Liu adopted approximation technique by explicit finite difference technique and implicit finite difference technique for the solution of fractional reaction dispersion equation involving Rich derivative. In the year 2006, Mischert solved the two-sided space fractional partial differential equation by employing the finite difference approach. Similarly, Boomer in the year 2008 developed a practical method based on operator splitting technique for the numerical solution of fractional order reaction diffusion equation. In the year 2015, Wu et al. Dealt with the lattice fractional diffusion equation in terms of Rich capital difference. Now let us introduce briefly about analytical technique for solving Rich fractional differential equation, that is optimal homotopy asymptotic method. Let us consider the nonlinear partial differential equation given by equation 4 with boundary condition given by equation 5. Here L is the linear operator, N is the nonlinear operator, and GXT is the analytical known function, and VXT is the unknown function, that is the solution of the equation 4. And B is the boundary operator, and capital gamma is the boundary of the domain capital D. So to apply the optimal homotopy asymptotic method, first we need to construct a homotopy function that is phi xtp, that is a mapping from D cross 0, 1 to R. That homotopy function satisfies the equation 6. This is called zeroth order deformation equation, where P lies between 0 to 1. P represent embedding parameter, and HP denotes the auxiliary function for P not equal to 0. When P is equal to 0, the auxiliary function H equal to 0. Now the homotopy function phi xtp is an unknown function. That function satisfies certain condition given by equation 7 and 8. When P equal to 0, then phi xt 0 equal to V0 xt, and when P equal to 1, phi xt 1 equal to Vxt. That means when P varies from 0 to 1, phi xt homotopy function, phi xt approaches from V0 xt to Vxt. Vxt is the solution of the governing equation that is given by equation 4, that is nonlinear partial differential equation. Now, how to determine the V0 xt? V0 xt can be obtained from the zeroth order deformation equation given by equation 6. This is the zeroth order deformation equation. By substituting P equal to 0, then we can obtain the equation 9. Then solving equation 9, we can obtain the V0 xt, the first component. And the auxiliary function HP is given by equation 10. HP equal to C1P plus C2P square plus C3P cube, where C1, C2, C3 represent convergence control parameter, which to be determined later. So the convergence of this solution, actually the solution of the equation 4 will be expressed in terms of a infinite series. The convergence of this infinite series, the solution depends upon this parameter C1, C2, C3. That's why these parameters are called convergence control parameter. Now the homotopy function, that is phi xtp C1, C2, C3, which is the solution of the zeroth order deformation equation 6, can be expressed as infinite series given by equation 11. So phi xtp C1, C2, C3 equal to V0 xt plus summation over I V1 xtp C1, C2, C3 into P to the power I. Now substituting equation 11 in the zeroth order deformation equation 6, and then collecting the coefficients of like power of P, we can obtain the first order problem given by equation 12. Now solving the first order problem given by equation 12, we can obtain the component V1 xt. Then again substituting the equation 11 in the zeroth order deformation equation given by equation 6 and collecting the coefficient of like to power of p to the power k, we can obtain kth order problem. Then solving the kth order problem, that kth order problem is given by equation 13. This is the general solution, the kth order problem, and solve the general kth order problem. Solving this kth order problem, we can obtain the general component, that is vk xt. The nonlinear term in this case will be expressed in terms of an infinite series with respect to the parameter p given by equation 14. Now, I already told the solution of this equation depends upon the convergence of this solution depends upon the convergence control parameter C1, C2, C3. Now let us take the approximate solution, that is mth order approximate solution of the equation, governing equation 4, that is the nonlinear PDE. This is the given by equation 15. So equation 15 gives the mth order approximate solution of the nonlinear PDE equation 4. So the VCAP is the mth order approximate solution. So VCAP xt C1, C2, C3 is given by V0 xt plus summation over I from 1 to m minus 1 Vi xt C1, C2, C3. Now substituting this mth order approximate solution in the nonlinear equation, given governing equation, nonlinear PDE, given by equation 4, we can obtain the residual function given by equation 16. That is, the residual function is here, Rm xt C1, C2, C3. Now, if the residual function Rm xt C1, C3 equal to 0, then obviously this mth order approximate solution, that is VCAP xt C1, C3 is an exact solution. But in practical case, it is not 0. The residual function is not 0. So the mth order approximate solution given by equation 15 depends upon the parameter C1, C2, C3 that values can be determined optimally by several techniques. One is called collocation method, another is called weighted residual method, another is a least square method. But here we shall I have applied the collocation method. So according to collocation method, the convergence control parameter C1, C2, C3 has been determined by solving the system of following equations. That is Rm xi tj C1, C2, C3 equal to 0 for ij equal to 1 to etc. So the solving this system of equation, we can obtain the convergence control parameter. And once we obtain the convergence control parameter C1, C2, C3 optimally, then we can determine the approximate solution, mth order approximate solution of the nonlinear PD given by equation 4. So now the convergence of this method, that is convergence of optimal homotopy asymptotic method, has been also proved in my paper, which is published in the year 2018 in the Journal of Computational Nonlinear Dynamics. In this theorem, I have proved that the mth order approximate solution given by equation 15, that is summation over k from 0 to m minus 1 vk xt, that converges if there exists a delta greater than 0 less than 1, such that mod of vk plus 1 less than equal to delta into mod of vk, where k greater than equal to k0 for some k0 belongs to the set of natural number. And what is v1, v2, v3? v1, v2, v3 are the solution of the, suppose v1 is the solution of the first order problem given by equation 9. V2 is the second solution of the second order problem given by equation 12, and V3 is the solution of third order problem. Next is let us consider a typical problem where the source term, that is the qxt, is given by equation 17 with initial condition ux0 equal to x square into 2 minus x whole square, where the domain of the equation, that is Reed's fractional reaction diffusion equation, is 0 to 2. With Dirichlet's boundary condition u0t equal to u2t equal to 0, where t greater than 0 less than equal to 1. Now first we shall apply the optimal homotopy asymptotic method. Now to apply the optimal homotopy asymptotic method, let us construct the following zeroth order deformation equation given by equation 21, which is satisfied by the homotopy function phi xt p c1 c2 c3 given by equation 22. Now, from the zeroth order deformation equation from equation 21, we obtain the zeroth order problem given by equation 23. Now, solving the zeroth order problem equation 23, we obtain the u0 xt given by equation 24. Similarly, we shall obtain the first order problem. How to obtain the first order problem? We shall substitute the homotopy function 22 in the equation 21, which is the zeroth order deformation equation, and then we shall collect the coefficient of like power of p, and then we can obtain the first order problem 25. Then solving the first order problem 25, we obtain u1 xt c1 given by equation 26. Therefore, the second order approximation solution of the fractional reaction diffusion equation is given by 27, where uxt equal to u0 xt plus u1 xt c1, where c1 is the convergence control parameter. So the convergence of the solution depends upon this parameter c1. The c1 parameter has been optimally obtained. Value of the c1 parameter has been optimally obtained by using collocation method. So using collocation method, I have obtained the value of the convergence control parameter c1 given by equation 28. Now, using the value of convergence control parameter c1, we obtain the approximate solution uxt. Now, the value of uxt for different value of xt has been tabulated in table 2 and 3 subsequently. Now, to apply the numerical method, we require to approximate the reach fractional derivative by fractional center difference approximation. So the definition of fractional center difference approximation is given by equation 29, and in the paper, Duman and Chelik in the year 2017, they have proved a lemma. In the lemma, it is shown that if the function fx belongs to the C5 bar, that is the space of continuous function whose derivatives are continuous up to fifth order, and also the derivatives up to fifth order belongs to the space L1R, then the reach fractional derivative of fx can be approximated by fractional center order difference approximation given by equation 32, and the order of approximation is order of k square. So where the alpha lies between 1 to 2. So the proof of this lemma has been given by Duman and Chelik in the year 2012, and they also show an interesting result that if the function psi star x is defined in a finite domain AB, and also the function phi star x belongs to C5R, and its derivative up to fifth order belongs to the space L1R, then the reach fractional derivative of phi star x can be also of order alpha, where alpha values from 1 to 2, then that can be also discretized by fractional central difference approximation, whose order of approximation is order of k square given by equation 33. Here, the domain AB will be a partition into m number of subintervals with a step size k equal to b minus a by n. Now, to apply the numerical method, that is second order implicit finite difference approximation, finite difference scheme, we shall first discretize the computational domain AB cross 0t by the grid points xi equal to ik for I equal to 1 to m, and Tn equal to nh for n equal to 0 to capital N, where spatial step k equal to b minus a by m, and temporal step h equal to capital T by m. Now let us assume that uxt belongs to C5 AB cross 0t. Then we shall approximate the first order partial derivative with respect to u by the central difference approximation given by this equation, whose order of approximation is order of a square, and it has been discretized at the point xi tn plus half. So discretizing the reach fractional reaction diffusion equation given by equation 1 at the interior mesh point, that is xi tn plus half, we can obtain the finite difference approximation, finite difference scheme given by equation 34. and this equation is valid at the interior mesh point. That's why it is valid for I equal to 1 to m minus 1 and n equal to 1 to capital N minus 1. Now equation 34 can be expressed in terms in a matrix form given by equation 35. That is I plus a into u to the power n plus 1 equal to I minus a u to the power n plus h into m to the power n plus half, where un is the m minus 1 dimensional column vector at the time level n, and a is a m minus 1th order square symmetric matrix given by equation 36, where a equal to b by 2 into k to the power alpha and b equal to h by 2 and j equal to g minus j, where gj is the coefficient of the Ricci fractional center fractional central difference approximation, and to show the implicit finite difference scheme given by equation 35 unconditionally stable, we require a function space given by equation 37. That is, that function space is given by capital lambda gamma, where capital gamma is AB cross 0t. So using this function space, I have shown, I have proved the theorem 1. Theorem 1 says that implicit finite difference scheme given in equation 35 is unconditionally stable. And also I have proved theorem 2, in which it has been shown that if u be the actual solution of the implicit finite difference scheme given by equation 35 of the problem 1 means Ricci fractional reaction diffusion equation, then the approximate solution, approximate numerical solution u bar unconditionally converges to the actual solution u when k that is a step size k and h time step h both tends to 0. And this proof has been shown in the paper given by reference 19. Next is numerical solution and discussion. The table 1 shows the absolute error obtained by using second order implicit numerical scheme for various values of x and t, taking the step size k equal to 0.01 and h equal to 0.5 for fractional order alpha equal to 1.8. Table 2 shows the comparison of approximate solution obtained by second order implicit finite difference scheme and also optimal homotopy asymptotic method for various values of x and t when k equal to 0.2 and h equal to 0.2 for fractional order 1.8. Table 3 shows the comparison of approximate solution obtained by OHM and implicit finite difference scheme of the Ricci fractional reaction diffusion equation for various points of t and x equal to 0.64 and taking the steps fractional order alpha equal to 1.8. So from this table we can see that there is a good agreement of result obtained by optimal homotopy asymptotic method and second order implicit finite difference method. Figure 1 shows the comparison of graphs obtained by implicit finite difference method and with the exact solution for time t equal to 5. Figure 2 shows the comparison of graphs for approximate solution obtained by implicit finite difference scheme with the exact solution when time t equal to 8. Next, I have solved another problem, that is a Ricci fractional nonlinear Solinger equation. This is the second model. The nonlinear Solinger equation are important equation in nonlinear evolution equation, which occurs in many areas of applied science such as plasma physics, quantum mechanics, fluid dynamics, nonlinear optics, etc. The nonlinear Solinger equation is an example of a universal nonlinear model which describes many physical nonlinear systems. So mainly the Solinger equation is generally used in the field of quantum mechanics to study the evolution and dynamics of wave packets. So in the Zhang et al. Used the space fractional Solinger equation to investigate the propagation of wave in the presence of harmonic potential as well as uniform acceleration. Oyelobi and Atagana has applied Fourier's pseudo-spectral method for solving the time-dependent Ricci fractional nonlinear Solinger equation in the presence of harmonic potential in 1, 2, and 3 dimensions. So let us consider the fractional nonlinear Schrodinger equation given by equation 38, where alpha is the Ridge fractional derivative which varies from 1 to 2 with initial condition ux0 equal to u0x, where domain of this differential equation is AB and t greater than 0 less than capital T. This equation has vast application in the areas of quantum mechanics that I already told. And here uxt is a complex valued wave function, where beta represents the strength of the local interaction and Vx is the potential function. Here it is taken as a particular function half gamma square x square, where gamma is the dimensionless stepping frequency in the spatial x direction. The Ridge fractional nonlinear Schrodinger equation has been solved using both analytical method, new analytical method that I introduced, that is modified optimal homotopy asymptotic method with Fourier transform, as well as a second order implicit finite difference method. The aim of this present work is to implement the approximate approach by fractional center difference approximation to discretize the fractional derivative in the Ridge fractional nonlinear Schrodinger equation. And the solutions obtained by these proposed methods has been compared in the tables and graphs. Let us consider the typical Ridge fractional nonlinear Schrodinger equation given by equation 39 with initial condition ux0 equal to e to the power minus x square by a, where a equal to 2 and the potential function Vx equal to 0.5 into x square given by equation 40. Now the initial condition considered here the commonly applied Gaussian wave packet, where wave packet at t equal to 0 is a Gaussian centered at x equal to 0. As t increases, the center of the Gaussian wave packet does not move from x equal to 0, so the packet spread out. Thus, according to the uncertainty principle of free particle, the system has the least uncertainty at t equal to 0, and uncertainty increase with time as the wave packet spread out. Now, to apply the approximate analytical solution, that is optimal homotopy asymptotic method. So first I applied the Fourier transform to the equation 39, that is Ridge fractional nonlinear Schrodinger equation. Now applying the Fourier transform, the equation 39 converted to equation 41. Then we shall apply the optimal homotopy asymptotic method. To apply the optimal homotopy asymptotic method, first we construct the zeroth order deformation equation given by equation 42, which is satisfied by the homotopy function phi ktp. And here the nonlinear term has been expanded in terms of Adamian polynomial. Now, from the zeroth order deformation equation given by equation 42, we obtain the zeroth order problem, and solving the zeroth order problem, we obtain u0 kt, which is given by e to the power minus k square by 2. Now, taking the inverse Fourier transform, we obtain u0 xt equal to e to the power minus x square by 2. Then, from the second order problem, we obtain u cap u1 cap kt. Then, applying the inverse Fourier transform, we obtain u1 xt c1, which has been obtained in terms of confluent hypergeometric function of first kind. So the first order approximate solution of Ridge fractional nonlinear Schrodinger equation for p equal to 1 is given by u xt equal to u0 xt plus u1 xt c1, where c1 is the convergence control parameter. The optimal value of convergence control parameter c1 has been obtained in this case using weighted residual method. And obtaining the optimal value of convergence control parameter c1, we obtain the approximate solution uxt. Now, the Ridge fractional nonlinear Schrodinger equation has been also solved by numerical method, that is second order implicit finite difference method. Now, to apply the second order implicit finite difference method, we first discretize the computational domain like the previous model, that is AB cross 0t by the grid points or mesh point xp equal to pk, where p varies from minus m to plus m, and tn equal to n into h, where n equal to 0 to capital N, with a spatial step k equal to b minus a by m and temporal step h equal to capital T by n. And let us assume that the solution function, that is uxt, belongs to C5AB cross 0t. And we shall discretize the first order partial derivative with respect to time t by central difference approximation, second order central difference approximation at the point mesh point xp tn plus half. So discretizing the Rees fractional nonlinear Solinger equation at the interior mesh point xp tn plus half, we obtain the implicit second order implicit finite difference scheme given by equation 43, where the local truncation error is given by rp to the power n plus half, which is order of h square plus k square. Now I have shown that this implicit second order finite difference scheme given by equation 43 is also unconditionally stable. That for that I have applied von Neumann stability analytic. And in the paper which is published in the year 2018 in the journal Numerical Methods for Partial Differential Equation, I have shown that the second order implicit finite difference scheme given by equation 43 is unconditionally stable and convergent. For that, I already told I have applied von Neumann stability analysis. Now next is numerical results and discussion. To discuss numerical results, I have computed two error norms. One is L2 norm and another is L infinity norm. These are the definitions of L2 norm and L infinity norm. So table 4 represents the absolute error for Rees fractional nonlinear Solinger equation obtained by modified optimal homotopy asymptotic method with Fourier transform and second order implicit finite difference scheme for various points of x and t, taking the step size k equal to 0.5 and h equal to 0.1 for the fractional order alpha equal to 1.5. So from this table we can see that there is a good agreement of result between modified optimal homotopy asymptotic method and second order implicit finite difference method. Table 5 represent the L2 and L infinity norm, error norm for different values of t when fractional order alpha equal to 1.5. Here also the errors are very less. So figure 3 represents the comparison of graphs obtained by implicit finite difference scheme and the optimal modified optimal homotopy asymptotic method with Fourier transform of equation 38, that is Rees fractional nonlinear Solinger equation for time t equal to 0.2. And figure 4 shows the comparison of graphs obtained by two proposed method for the Rees fractional nonlinear Solinger equation for time t equal to 0.5. And this is figure 5 represents the comparison of graphs obtained by two proposed methods for Rees fractional Solinger equation for time t equal to 1. Figure 6 shows the 3D surface solution for mode of uxt obtained by modified optimal homotopy asymptotic method with Fourier transform. Figure 7 shows the behavior of solution obtained by second order implicit finite difference scheme for different values of alpha, for alpha equal to 1.25, alpha equal to 1.5, and alpha equal to 1.99 when time t equal to 0.5. Figure 8 shows the behavior of the solution obtained by implicit finite difference scheme for different fractional order alpha when time t equal to 1. Now the conclusion. The conclusion is that the Rees fractional derivatives is approximated by utilizing fractional center dependence approximation technique. The second order fractional, second order implicit finite difference technique is implemented for solving Rees fractional reaction diffusion equation. The local truncation error is second order because it is order of k square plus a square. For the purpose of comparison, the Rees fractional reaction diffusion equation has been also solved by analytical method, optimal homotopy asymptotic method, to ascertain the analytical approximate solution to the Rees fractional reaction diffusion equation, where the convergence control parameters are determined by collocation method. So to establish the efficiency and accuracy of the proposed method, the results has been obtained by two proposed methods has been cited in tables and graphs. The advantage of optimal homotopy asymptotic method is that it allows the fine tuning between the rate of convergence and convergence region by suitably identifying the optimal value of convergence control parameters C1, C2, C3, etc. The second order finite difference scheme has been applied for Rees fractional nonlinear Solinger equation. For the purpose of comparison of result, one new technique, that is modified optimal homotopy asymptotic method with Fourier transform, has been applied. The result obtained by the two proposed method has been exhibited in tables and graphs in order to show, justify the accuracy and efficiency of the proposed technique. The present success of these two proposed techniques for the rich fractional differential equation established that the proposed techniques are useful tool for solving real physical problem in science and technique, science and engineering. The advantage of the proposed modified optimal homotopy asymptotic method with Fourier transform is that it allows the fine tuning of a convergence region and the rate of convergence by suitably identifying the convergence control parameter. The solution obtained presented in the table manifests that there is a good agreement of results exists between the solution obtained by the two proposed methods. These are the references. The reference 19, in this reference 19, I have solved the first model problem, that is reach a fractional reaction diffusion equation. And this paper has been published in the Journal of Computational Nonlinear Dynamics. Reference 29, in this reference 29, I have solved the second model problem, that is this fractional nonlinear Schrödinger equation, and that paper has been published in the numerical method for partial differential equation. These are my few books on fractional calculus. On interested readers can consult these books for getting more knowledge in rich fractional differential equation and also fractional calculus. Thank you for watching my presentation.
Thank you, Professor Ray, for your nice and informative talk. Any questions from the audience? Any questions or comments?
Sir, good morning, sir. This
Yes.
is a wonderful talk, sir.
Yes.
In these two model, you have used implicit finite difference scheme.
Yes.
Rather than other finite difference scheme. Is it any specific relation with scheme and Riesz fractional derivative, sir?
No, actually, to apply why no. Your question has two aspects. One is why I have applied implicit finite difference scheme, because I have applied implicit finite difference scheme in the with the objective that the convergence will be unconditional, the scheme will be unconditionally stable. This is the one reason. Another reason, another thing is that to apply the implicit finite difference scheme, I have to discretize the Riesz fractional derivative. So to discretize the Riesz fractional derivative, I need a suitable definition, a suitable discretization technique. So for that, I have applied fractional central difference approximation. I didn't apply any other approximation technique like Gruan-Letnikov or weighted Gruan-Letnikov, because those are in those approximation, order of approximation is first order.
Yeah.
But here in the fractional center difference approximation, it is second order approximation.
Okay. Thank you, sir. Thank you so much.
Yeah, Professor Santanu, I have one question.
Yes, sir.
We have generally seen, and it has been shown in literature also, and we also discussed in my talk, that if there is a reduction in the fractional derivative order, then there is an issue with the convergence. So did you also notice something with this rise fractional derivatives, or and if yes, could you suggest anything related to that?
No. In my approximation, I didn't reduce anything. I didn't truncate. That's why I have taken the second order approximation. I didn't reduce anything. If I reduce, it is true. If I reduce, then physical phenomena cannot be realized more practically. It is true, but I didn't reduce anything. I didn't truncate anything.
Okay. So
that's why I have taken second order approximation. Okay. Instead of any other approximation like Gruan-Letnikov or weighted Gruan-Letnikov, any other approximation, I have taken fractional central difference approximation.
Okay.
This is the reason.
So it works for any, the numerical method works for any value of fractional derivative.
Yes, sir.
Any order, I mean to say.
Yes, sir. Even recently, I am working on variable order.
Okay.
It also works.
Okay. Even that is also an interesting area now. Variable order and complex order also.
Yes, sir.
People are
Yes, sir.
working
Yes.
on that.
Yes.
Thank you, sir.
Thank you, sir. Thank you.
Any other questions? I think as usual, Islam has raised his hand. As usual, you want to ask him question? Any other questions from the audience? Anybody want to ask him question? Okay. I think there is no question. So, Professor, thank you very much once more for your nice and enlightened talk. And let us have a round of applause for him.
Thank you, Professor Dilip Kumar. Thank you, Professor. Thank you, Madam.
So,
KG, Madam.
So thank you, Sachin sir, for inviting me to chair this session, and I request Sachin sir to take over the session. Thank you.
Thank you, Dr. Shantanu Sahare, for
Thank you, sir. Thank you, Professor Jaferi, sir.
And thank you, Dr. Dilip Kumar, for chairing this session.
Thank you, sir. Thank you,
Yes.
Professor Das.
Thank you, sir.
Thank you, Madam. Thank you.
Thank you.
Okay, Madam.
There is one announcement for participants. In the valedictory session, we expect feedback from participants. So it will be 2 to 3 minute talk. So those who want to present their views, please email me so that we can arrange accordingly. So next session will start after 5 minutes. I think chairman is also there and speaker is also there. So if they are ready, we can start right now or we can have break. So Professor Subir Das.
Good morning, sir. Good morning, sir.
Is it okay to start now or?
Yeah. I have no problem.
Okay, fine. So I invite Dr. Krunal Kachia, Charotar University of Science and Technology.
Would you give me just 1 minute? Okay.
Sure, sir. Sure.
Ritika. Yes, sir. Okay.
Welcome everyone to next session. I invite Dr. Krunal Kachia from Charotar University of Science and Technology, Gujarat, to chair this session. Over to you, sir.
Thank you, sir. Am I audible?
Yes, sir.
Good afternoon. Good morning to all. I really thankful to Dr. Sachin and his team for giving me this opportunity and to be a part of this such a wonderful event. So it is my immense pleasure to introduce our eminent speaker for the session. Professor Subir Das is working as a professor with the Department of Mathematical Sciences, IIT BHU. His areas of research are mathematical modeling, fractional calculus, dynamical system, fracture mechanics, porous media. Till date, he published 196 research articles in reputed international journals. The number of citations of his article is more than 3,150, out of which 2 articles have been cited in the journal Nature. He had been academic visitors in number of universities such as NUS Singapore, NTU Singapore, University of Malaya, Malaysia, City University and Hong Kong, Polytechnical University, Tokyo University of Science, Japan. He has attended and delivered lectures in various international conferences in USA, Japan, Switzerland, Italy, France, England, Scotland, Greece, China, Taiwan, Singapore, Malaysia, South Africa, Thailand, and Bangladesh. Recently, the UCSI University, Kuala Lumpur, Malaysia, has conferred him the position of visiting professor. Professor Das has been figured among the world top 2% scientists in a world database created by Stanford University, California, USA. Professor Das has supervised 25 scholars for their doctoral program and 28 students during their postgraduate program. Presently, 12 research scholars and 4 postgraduate students are working under his supervision. He has the experience to work Deputy Coordinator SAP UGC. He has completed research project from funding agencies like BARC, Government of India, SERB, Government of India, and TCS India. One of his research articles has just published in highly prestigious journal Proceedings of the Royal Society of London, Series A. His institute IIT has conferred him the Excellence in Teaching Award for the session 2016 and 17. Sir, warm welcome to you. And now over to you for the session.
Thank you very much. Hello. Hello, can you hear me?
Yes, sir. Yes, sir.
Yeah. Thank you very much. So, may I start now, sir?
Yes, sir.
Yes, sir, please.
With the kind permission of the chair, starting.
Yes, sir. Yes, sir. You can start.
Good morning to all the participants and organizers. First of all, let me wish you all a happy and prosperous new year. I want to extend my gratitude to Dr. Sachin Bhalekar for inviting me to deliver a lecture in this great show of fractional calculus, which is ICFC 2022. Myself, Subir Das, associated with the Department of Mathematical Sciences in the Institute of Technology, PH, Varanasi. My topic of today's lecture is the study of two-dimensional nonlinear fractional order transport problem arising in groundwater contamination. Actually, in the topic, you see there are written two-dimensional, nonlinear, fractional order, groundwater contamination. So it is my duty to clarify all the things why I had it in the title of my talk. So I have to justify that one. Now you see that rehabilitation will be very difficult if groundwater gets polluted in general. So it is important to model the contaminant movement in aquifers to understand its impact on human health and environment. To accomplish this, a thorough understanding of physical, chemical, and biological processes that control the transport of solute in groundwater is necessary at the outset. So it is very much needed. It is also needed a careful attention for describing the problem domain, the boundary conditions, and also it is needed to adopt good, appropriate numerical methods for solving the numerical groundwater models of the field problems. Now, the general solute transport model is the reaction advection dispersion equation, but sometimes it is called advection reaction diffusion equations. Since why these equations are very much necessary to study for groundwater contamination, because it has the combined effects of advection, dispersion, reaction processes. Now, mathematically, this equation is this type of equation is represented by the equation 1, where D is the diffusion coefficient. Now you see, I have told you I have to justify all the terms why it is fractional. What is the need of considering the fractional order system? You see, the fractional order system or diffusion equation are obtained by people know it, that are replacing with a fractional order. That one, because we know that fractional order system has the advantage of greater degree of flexibility of the system. It is written greater degree of freedom, but it is better to say the greater flexibility of the system. Now, another important phenomena of the evolution equations. Why I will say that these are the evolution equations? I am coming to the later. It generates the fractional Brownian motion, which is the generalization of Brownian motion. Also, you see the integer order system is a local operator, whereas the fractional order system is non-local. Why it is non-local? Because it represents the non-Markovian process. What is the non-Markovian process? Non-Markovian process means future. In Markovian process, you see future only depends on the present, but in non-Markovian process, it not only depends on the present, but all the history of the past. So there is the memory effects. Due to this memory, the fractional order system is more acceptable than as compared to the integer order system. Now you see the why we calculate the fractional order AD for contaminant transport in groundwater. You see in the classical solute transport, divide the experimental result or break through the curve showed in anomalous diffusion. Actually, in fractional order system, we get the anomalous diffusion equation. Also, if the classical that is integer order advection diffusion equation gives the fiction transport, whereas the fractional order system gives the non-fiction transport. Now I want to discuss the stochasticity, because people say, why fractional calculus? Why the fractional order model? So before I go to the stochastic nature of the fractional diffusion equation, I just want to show one example. Wherever I deliver lecture on stochastic process or fractional, I start with this example. In stationary process, the first moment depends on time, and the covariance of xt and x and y all depends on difference between x and y, and the covariance of the system is, that is the second moment is finite. If the first moment does not depend on time, then that is called erodic process. So the process which is neither stationary nor erodic is called the evolutionary process. Now, let me start with a stationary process. They consider a random variable xt like this: a cos omega t plus b sin omega t, where a and b are uncorrelated random variable, that is e of expectation of ab is equal to 0, and it each having mean, that is mean 0 and variance 1, that is ea is 0 and and variance means e squared minus ea whole square, that is e squared is 1. Now we have seen that if I consider the two random variables x and y, then x bar, because we have to find the covariance. So we want to correlate to two data coming from the random variables x and y. If we calculate, if first see the moment, moment, that is the mean of x is 0 and mean of y is 0. So covariance of xt and ys, if we calculate, that is e of x minus x bar into y minus y bar. Since x bar and y bar is 0, so if we put suppose cos omega t plus sin omega t plus a cos omega s b sin omega, and we know e squared is 1 and e is 0. So if we calculate, we get cos of omega into t minus s. Now you see, since the first moments are 0, so covariance of xt and ys becomes e of xt ys. So if you put capital X is equal to capital Y, then we get the second moment. So second, you see the second moment is, if we put t equal to s cos 0, that is 1, so it is finite. So you see the first moment 0, second moment covariance depends on t minus s, and the second moment is finite. So it is a stationary process. Now we have to check whether the fractional order model is stationary or evolutionary. Now Einstein's theory of Brownian motion reveals that the mean square displacement of the particle moving randomly is proportional to time. But after the advancement of fractional calculus, it is seen that mean square displacement of anomalous diffusion del alpha u by del t alpha equal to del t u by del xt is equal to is proportional to t to the power alpha. So second moment is proportional to t to the power alpha. That means it is not finite. So we can say this is an evolutionary process. That's why the fractional, but even the diffusion equation is the evolutionary process. So fractional order model is diffusion equation is also evolutionary process. Now I have found the stressed Gaussian because non-Gaussian shape. Another thing is it not only non-Markovian, but fractional order is also the non-Gaussian. So non-Gaussian shape of the diffusion equation will be like this. I have calculated because due to the constraint of time, I have not shown the exercise. If one is interested, you can go through my papers, articles. You see, since this presentation contains all of my personal works, that's why I'm not given any references. Even in Google Scholar, you can see the papers. Now, the stressed Gaussian expression is given there. Now, fractional order derivative has a physical meaning related to statistics of waiting times, according to the Montreal-Weiss theory. Now, we know the classical diffusion equation is obtained. First, we will we'll go through a simple model, then we will come to the complicated model. So we know the classical diffusion equation. Classical diffusion equation is obtained through the combination of fixed law and the mass balance equation. So if we these two equations combinedly gives del u del t is equal to d into del t u del x, where d is the diffusivity constant. Now in 1972, during literature survey, I have shown Norwood. He took a close look of the fractional Fick's law, like J is equal to minus D of T, where the kernel is given by 1 by gamma alpha minus 1 or T minus tau. Sorry, here is a mistake. It is T minus tau whole to the power alpha minus 2. Now it gives me some pain of during the modeling of fractional order model. As you see, gamma alpha minus 1 comes in the denominator. Now Professor Geiji, respected madam, already yesterday during her deliberation of lecture, she has highlighted on gamma function. Without gamma function, actually, the modeling of fractional calculus is impossible. So one thing I want to mention here, that gamma function, gamma n, which is integration 0 to infinity to the power minus x to the power n minus 1 dx, is exists everywhere. Gamma n exists everywhere except at n equal to 0 and negative integer. Just sometimes people ask gamma negative, how it exists. Suppose I am just giving a simple example. Gamma n plus 1 equal to n gamma n. Put n equal to minus half. Then gamma half is equal to minus half, gamma minus half. So gamma half is root pi, so gamma minus half is equal to minus 2 root pi. So it is in that negative non-integer value we can get. But gamma function does not hold good for 0, minus 1, minus 2, minus 3. Okay, so not negative integer. It does not exist for negative integers and 0. So now you see, if gamma 0 does not exist, because if you see the right hand limit of go through the graph of gamma function, right hand limit is plus infinity, where the left hand limit is minus infinity. The integral does not exist. But we consider that gamma 0 is equal to infinity. Why? Because you see tan 90, tan pi by 2. It does not exist. But for the sake of mathematical calculation, we consider tan 90 is equal to infinity. Because tan pi by 2 minus is plus infinity, tan pi by 2 plus is minus infinity. So it does not exist. But for the sake of mathematics, we have considered tan 90 is equal to infinity. Like that, gamma 0 does not exist, gamma minus 1 does not exist, gamma minus 2 does not exist. But for the sake of mathematics, we have considered gamma 0 is equal to infinity, gamma minus 1 equal to infinity. So if we draw 1 by gamma n against n, then we see we get a continuous curve. So what I want to say, 1 by gamma n is much preferable than the gamma n. That's why the kernel k of t minus t of tau, where 1 by gamma alpha minus 1 has come, is self. So the order of expression is highly accepted. Now we have put it here in the mass balance equation, and we have got del alpha u del t alpha equal to del t u by del xt. Now sometimes it is seen that wherever first order derivative we put alpha and 0 less than alpha less than 1, that is what is a fractional order, fractional PDE we say. But I always say that modeling is necessary to convince the people. The modeling, how it is coming, whether it is justified. So we should say see. So here you see the fractional order diffusion equation is justified because I have modeled it logically. Now next our aim is to show whether what is the interpretation of this. Now a stochastic interpretation I want to give here. Stochastic interpretation, this is a linear equation. Okay. Now, so one thing is that you say why you are working, why you are showing that stochasticity of linear, because whatever the linear equations of that, if you go to the non-linear, that the non-linear, the properties of linear exist in non-linear, but converse is not true. So linear form is calculations of stochastic analysis of linear form is sufficient to predict the non-linear equations. So we have taken Laplace transform, and we have got the expression of uxt in the transform plane. Now we know that uxt is a probability density function. So minus infinity plus infinity uxt dx is 1. So we have calculated As. Now we have got the expression of E bar xs because As is now known. Now we have to we have calculated the to get even moments in the transform plane. To get moment in the transform plane, which is given by that one, gamma 2k plus 1 by s to the power alpha k plus 1. Now we have converted, we are back to the time domain, and by using the Laplace inversion. Laplace of t to the power n equal to gamma n plus 1 by s to the power n plus 1. So Laplace inversion of 1 by s to the power n plus 1 is gamma n t to the power n by gamma n plus 1. That formula I used and found that 2kth moment at the 2kth moment in the time domain, which is given there. So if we put k is equal to 1, that is the second moment. Second moment you see is proportional to t to the power alpha. So what we can say, this is an evolutionary process. So fractional diffusion equation is a evolutionary process. Now my interest next to whether if I sir, can you hear me? Hello.
Yes, sir. Yes, sir.
Yes, sir. Okay, audible, no? Okay. Now let us consider. We have to consider the advection diffusion equation. Now we have to say which type of model and how much that second moment varies with time. That is my intention. So I have taken here advection term minus nu into del u by del x, where nu is the advection term and minus lambda u. Lambda here greater than 0, so it is a sinc term. Correct. So I have taken the Laplace transform here, and we have got the expression of u bar xs is like that. Even we can calculate in the time domain also. But as the previous one, I have calculated the 2kth moment in the transform domain, then back to the time domain. So here you see 2kth moment is given by gamma 2k plus 1 by this. After a mathematical manipulations of equation 5, we get the two-kth moment is approximately equal to given in equation 6. So we apply, we bring it to the time domain where we got the two-kth moment in the time domain is t to the proportional to t to the power 2k plus 1 alpha by 2 given in equation 7. So if we put k is equal to 1, the second moment is proportional to t to the power t alpha. So it is also evolutionary process, but whenever you see only the diffusion equation was there, only the diffusion term was there, you see the second moment is proportional to t to the power alpha. Now after adding the advection term and the reaction term, it is proportional to t to the power 3 alpha by 2. Now next question is why nonlinearity comes in the transport in groundwater problem? Because biodegradation is an important aspect of contaminant probe, as many compounds may be eliminated by natural biodegradation. Now, the solute transform with nonlinear biodegradation occurs in many situations involving inorganic chemical, metal contamination in soil and the groundwater systems. So when the contaminant is subject to nonlinear degradation or decay, it is characterized by, it is actually modeled in terms of the differential equations which are nonlinear. So that's why in the transporting groundwater problem, nonlinearity is a big role. So if we model any contaminant mathematical modeling contaminant transporting groundwater, nonlinearity will come. We can't avoid it. It will either come semi-linear or quasi-linear or highly nonlinear. Now the question is why it is you see what was my topic? Two-dimensional. So whatever I have told you that this is for all one-dimensional. Now I have to come to the non-dimensional, non-linear fractional order model. So I have just studied an analysis, a 2 plus 1 dimensional solute transport equation in porous media. Now why it is 2 plus 1? If you see my model, you will see the time is one dimensional and the space is 2D. Space is 2D. So the model is given as del alpha u by del t alpha is equal to this into plus this minus the advection term is there plus lambda RU. Here you see RU is nonlinear. RU is nonlinear. That means this equation actually is the semi-linear. Now, when I did it on the project in Board, this type of problem was given by them. So I acknowledge their contribution, the contribution of my PC, Dr. Monish, for modeling this space-time fractional order nonlinear advection reaction diffusion equations. Now all the initial condition and boundary conditions were given by them. So under this mixed boundary conditions, we have to solve this type of equations. Now you say why you have considered the semi-linear, because we have to go first through the simple model, because we can't go through the what you call linear model, because I had the ground contamination problem is always non-linear. Now the nonlinearity I have kept in the reaction term. If here you lambda less than 0, it is a sink term. If lambda greater than 0, this is a source term. So lambda less than 0, it allows us to damping the solute concentration. So with a proper choice of reaction term, we have the flexibility of damping the solute transfer. This is the beauty of choosing the reaction term. Now, during solution of this, we have taken the approximate solution by using the shifted Lysander polynomial like this. Here you see we have used the Kronecker product. Basically, the Kronecker product represent the linear transformation. Suppose A and B, they are the Kronecker product. A and B are the two linear transformation from B1 to omega and B2 to omega 2. Then the Kronecker product of A and B, you will map B1, B2 to W1, W2. Actually, this type of a Kronecker product has good applications in signal processing, image processing, and quantum computing. So, we have used this Kronecker product here, and to approximate all the time fractional derivative or spatial fractional derivative. Here we get two matrices. One is identity matrix given by capital I. Another is shifted Lysander operational matrix, which is given by D of beta. Now you see that we have formed a operational matrix here where the first alpha rows are zeros. Now we have substituted all the approximations in the in our model as well as in the initial and boundary conditions, and we have got the equations 10, 11, 12, 13, 14. Now we have collocated those points m-1 cross m-1 into m+1 points, and here you see after the collocation these equations 10 to 14 are transformed into a system of m+1 cross m+1 whole squared nonlinear algebraic equations. So now these nonlinear equations can be solved by using the Newton method, which is inbuilt in mathematical software. So we have calculated all the u and then substituted there, and you have got the expression of u. Now next is we have proposed a method for solving equation 1 under the initial condition and boundary conditions given in 2 to 6. Now it is our duty to validate our proposed model with the existing results. Otherwise, people will not accept the beauty, the efficiency, the effectiveness of our proposed method. That's why what we have done, actually, there is no particular, I went to the literature survey and I have not found any analytical solutions or numerical solutions of this type of equations for any particular case. So it gave me some pain of validation. Next, what I have got, I have certainly that the particular case of my model, that if we put alpha equal standard order, alpha is equal to 1, S is equal to 2, beta is equal to 2, sorry, it is not S, it's a beta. Beta is equal to 2, D1, D2 is equal to 1, and the advection coefficients are 0, then it converts to the, it is converted to the integer order Fisher equations, which has the exact solution. You see at the bottom, under the boundary conditions, this. So what we have done, we have solved that one with our proposed method and compared our method with the exact solution given there. So how we have compared? We have considered the L2 norm, L2 error actually, L2 error between our proposed method and the exact solution. And we have seen that even for small values of n, order of the matrices, small order of the matrices, we get the error as 10 to the power minus 4, 10 to the power minus 6, 10 to the power minus 8. So if we increase them, we can get lesser error, and that tends to 0. So our conclusion, what will be our conclusion? Number one, even small values of n, we get small values of the error, and number two, that our proposed method is very efficient and effective of solving the semilinear fractional order, two-dimensional fractional order model. Now, our next target will be, since we have solved for some semilinear, now next our aim will be solve the quasi-linear or highly non-linear fractional order models. This is okay up to this. Now it is my duty to show you that. Thank you very much. Hello. Hello.
Yes, sir. Thank you so much, sir.
Just a minute.
Yes, sir.
I have to. Yes, sir.
So thank you so much, sir, for your wonderful talk. Now, with your kind permission, I would like to invite some participants for their questions. So from the participants, any question? Yes, sir, you can ask.
Yes, sir. Sir, good morning.
Good morning. Sir, it's wonderful talk.
Thank you.
So at the end of the slide, you have given an exact solution when alpha is equal to 1, the Fisher's equation.
Yes, sir. It is existing. It is existing.
I understand that you can also have one more solution. I mean, you have written one exact solution.
Exact solution is there available in literature, sir.
Yeah, that's fine. See, apart from this, you can also construct additional solutions.
Yes, sir.
Okay. So that's my suggestion.
Yes, sir. Another thing was our aim was to validate the result, whether the proposed method for our satisfaction at the same time to convince the people.
Yeah, excellent.
Our method is okay. So we have solved that model under the given boundary conditions, and we have compared our proposed results with the existing results, and we have got that error is very less. Okay. That's why our method is very efficient and effective.
So I completely agree. What I want to say is, you have one solution already, and there are one more solution is available. Maybe you can also use to make use of your method.
Sir, your voice is coming in discrete way.
No, see, I mean, your method is very efficient. I mean, it's perfectly correct. And right now you are having one exact solution.
Yes, sir.
And with that you are checking your method. And you can also, since this equation admits one more exact solution,
okay,
so you can also check. That's all. That's my point.
Okay, sir. Because I have not yet communicated this one, I will do it. Because I am just trying, just got the project. That's why I am trying. And you see the I have, sir, gone through the literature, and I have not seen any particular form of that fractional model, even that form. So that's why I have to go to the linear model, to the integer order model, classical model, for particular cases, actually.
Okay, thank you.
Okay. I'll also see another example. Thank you very much, sir.
Thank you. Maybe I can share that solution later.
Okay. Yes, sir. Yes, sir.
Thank you.
Okay. Thank you very much, sir.
Any other question?
Good morning, sir. I am Mohammad Parvesh Alam.
Yes, please.
My question is different from it. If you suppose in time derivative we add a multi-term time fractional derivative, then what happened the transport process, sir? Actually, my question.
Multi-term.
Yes, sir.
Yeah. Actually, I am telling you that in fractional order and integer order.
Fractional order, sir. If I take a
fractional order, sir, I have told you that 2 plus 1, that is in one-dimensional fractional order, time fractional and space fractional. Beta 1 less than beta less than 2. And with advection term and the reaction term, is particular cases are not available. So you can see this is actually the start of the fractional model in groundwater. You can see one-dimensional, you can get lot of particles. During last 5 years, we have also contributed a lot. But in two-dimensional, it is very hard. You see, I have solved for a semilinear. I have not yet communicated it. I am telling you, next I will go to the quasi-linear and highly non-linear. So multi-term is, later we'll see, but it's not now, it's very hard now.
Sir, one question more, sir.
Yes, sir.
If we suppose the space direction is the ordinary and only time fractional, sir.
Yes.
If we take in time direction multi-term fractional order, what is the effect of multi-term, adding the multi-term and on the single term derivative?
Okay. You are saying that space is integer.
Ordinary, sir.
Integer and time is multi-word.
Yes, sir.
I can't. Because I have not yet done anything, so it is very. It will be not justified for me to highlight anything because now let me allow to restrict myself in 1D because in groundwater model is highly unpredictable. And another thing is that you have seen, I have shown that the stochastic nature of that. So I have shown stochastic nature. So you see the second moment. Second moment is highly changing with time, and if it is if there in the model the effect of advection term and reaction term, you t to the power alpha 2 t to the power 3 alpha by 2 say drastically change. So I think multi-order for the sake of mathematics you can do, but when you will see the stochastic nature, you will see it is sometimes it's not so easy to do it. It is my opinion. Modeling, as I see that any equations they are replacing by alpha without doing any model, without justifying the model. I do not do that. Whenever I can model, then I do it. So that's why I am telling, because I always discuss the stochastic nature, and time is so randomly changes. Time is changing. Second moment is changing randomly. Anomalous diffusion. Na? So that's why it is very hard to keep safe in that way what you are saying.
Okay, then. Thank you so much.
I have one question.
Madam, Namaskar.
Namaskar.
Madam.
So you see, in fractional dynamical systems, what we observe is that intersection of trajectories. So
yes,
unlike, so do you observe in this groundwater modeling?
No. Only, madam, what we are seeing, only I also do that, madam. I have also, I do some works on dynamical system. You have seen. Here in porous media, whatever we get, we are interested to get the subdiffusion or superdiffusion. Madam, I want to just highlight one thing is that del alpha u by del t alpha is equal to del 2 u by del x2. Suppose advection reaction is there. You see, it is defined as when 0 less than alpha less than 1. It is subdiffusion. Alpha is equal to 1 is the standard integer order. Alpha greater than 1 is the superdiffusion. Alpha is equal to 2 is the ballistic equation. But you know, if you write del alpha u by del t alpha is equal to del x of u del x, that is a nonlinear. Even for alpha less than 1, it gives the super diffusion. So we always, what we have got, we got only subdiffusion and super diffusion, nothing more than that.
Okay.
So, but then is there any possibility that you encounter a super diffusive scenario in groundwater contamination?
Yes, sir. In mostly we get the super diffusion. But whenever you see in groundwater problem, engineers prefer to see subdiffusion. Correct, na?
Okay.
So if in any region, if you do not do the subdiffusion, they will not accept it, because this is my project related. So that's why our always interest to find the range of alpha, so that we get a subdiffusion. And that's why you see the reaction term. I have added a reaction term with a proper choice of reaction term. That is sink. So we can damping that one. Damping, and suddenly we get a subdiffusion. Okay. So any not so easy.
Yeah. Any particular reason to choose beta? I think it is a space derivative fractional order. I think beta.
Yes, sir.
So any particular reason to choose it between 1 and 2?
No, sir. What I have seen in one-dimensional, two-dimensional, I have not done much. I'm just coming to that one. The one-dimensional, I have seen del alpha u by delta. If alpha is close to 0, that is 0.1. It behaves abruptly. It does not give you a good result. But if you see alpha is equal to 0.4, 0.3, 0.4, even 0.4. So in most of the papers, you will see alpha, they have taken alpha is equal after 0.5. Similarly, beta close to 1, you will not get good result. Why? I don't know.
That's the whole, sorry to interrupt you, Dr. Subir.
Yes, sir.
That's the whole scenario. And I think there is no other than Professor Genji madam to comment on this. These smaller values of fractional derivatives,
yes, sir,
they really create a big problem. I mean, they had created, but to our, we are lucky that
actually, I don't know about the physical interpretation, but one can develop numerical methods which converge for very small.
Yeah.
My question was, if this is okay that it describes super and subdiffusion, but if you just evolve this and treat this as it is after all a deterministic proper differential equation.
Yes, madam.
So when you are studying groundwaters, do you observe intersecting lines? Because that is what is happening in fractional order dynamical systems. Your lines intersect. Intersect means they in ODs you don't see intersections, no, that flow lines don't intersect, but here they do intersect. So I mean to say or there are cusps kind of situations. So
madam, intersect means alpha is equal 0.5, 0.6. This
it doesn't matter, whatever is, it is irrespective of alpha. You
okay.
can get so I mean to say, when you are modeling say something through porous media and all that,
Correct.
so physically do engineers observe such flow lines which intersect? Maybe in turbulence, or I mean, then my point is how to comprehend this thing, because definitely we have mathematically proven that whenever there is a zero of Mittag-Leffler function, when even linear dynamical system, fractional or dynamical system, whenever there are zeros of Mittag-Leffler functions, because Mittag-Leffler function is not always invertible, so flow lines intersect. So where is the physical situation where we can say, oh, this is the situation there, and we can now apply or formulate this with this fractional differential equation? That will be fantastic in my opinion.
Madam, what sir was asking, why it is close to alpha is close to 0 or beta is close to 1. What is the problem? I think in the stochastic modeling, you have seen the second moment. One thing I want to just mention that that time a stochastic process is not there, and without knowing that, Einstein predicted, you see, the second moment varies with time. So whenever you go it is for fractional order, it is t to the power alpha. So if alpha is equal to close to 0, suppose 0.1, t to the power 0.1, I think t to the power 0.1, t to the power 0.1, t to the power 0.2, that may give trouble. I think.
No, that is physically, what does it mean? That means there is not much change. No, I mean alpha is 0.01.
Not very little change. Very little change. Very little.
There is physically, what does it mean? I mean, very mild kind of dynamics, or what, I don't know physically.
But that is the what is going on, man.
Acha, so you do get such situations.
Yeah.
Acha, okay.
I think Professor Mears, Chairita and all that, they have got some papers on this groundwater anomalous
Contamination.
diffusion, right?
Okay.
But mostly, sir, you will see all are 1D, one dimension.
Okay.
One dimension. Two dimension is very
and actually, let me tell you this subdiffusion, super diffusion interpretation is valid for one dimension. So for 2 dimensions, still there is lot of things have to be proved.
Madam, actually in 3 dimensional, if you go to the 3-dimensional graph, I have not, because time constant, due to time constant, I have got a graph like this, correct now? And I have checked, suppose converted to beta 1, beta 2 equal to 0. So if we go to the beta 2 value, or beta 2 value, we are seeing that it is making sometimes subdiffusion.
Because all this super, that interpretation is through statistics. So probability distributions and all that.
Yes.
I think
so,
they
but
use
that
continuous
also
time random
proves,
walk. Continuous
Yes,
time
yes,
random walk favors.
yes,
but
sir.
all that is only done for 1 dimensions.
Random
so that is
walk
the
is there.
objection, in fact, that many people still don't take fractional modeling so seriously. You want everything in R3, right? You want your Gauss law to be defined through that, and but for that you require different machinery. I mean, this one-dimensional machinery is not enough.
Geji madam, there are papers by Machado and all that where they have given fractional order versions of electromagnetics and all those things.
Yes.
So it is available. So
Now a lot of engineers.
Even Tarasov.
It is available, but I mean, mathematically, is it approved? I mean,
yes,
you know,
I don't know whether it is approved or not, but I think there is a book by Vasily Tarasov who talks about, who has got a dedicated book about all these, even quantum mechanics, everything. It is available.
That is true, but I mean, are there then probabilistic interpretations? And because there are many times speculations, and you know, it is all a formative area. That's what I mean to say.
That is
I'm not an expert on everything.
Machado has contributed a lot, but on 8th November, he has died, you know.
He has passed away. So, yeah, we should actually pay homage to his.
Madam, I want to just mention here, I have basically, my PhD and postdoc was on fracture mechanics. But I have come here in this area and started seeing the 2 persons. You people are there. One is you, madam, and another is Professor Sahadevan. And I am fortunate that you both are here. You people stay. And now the young people are coming to fractional calculus. More people are coming in different years. So Sachin Bhalekar, he is also contributing a lot, and I know the other persons. So, madam, you the people, you both are icons for our fractional calculus. So,
agreed. True.
Sir,
thank you. Thank you.
Madam, you know I am very mediocre, but work hard. So, I'm trying.
We can keep it up, and I have no hopes that, I mean, we have no big croc session in India, young, active persons. So everybody should come forward and arrange such meetings. That will keep us going.
Okay.
You know, through discussions and through interdisciplinary discussions also. So I am also very happy to see all of you together, at least virtually.
I'm glad to see the Professor Sahadevan and you are here.
Actually, it is motivation by Varsha.
Motivation. It is a great motivation.
Yes. she started arranging such.
Even Professor Jafari. Professor Jafari has lot of contribution in fractional calculus.
Yeah.
Professor Jafari.
One such person, I mean, you
Jafari
can say a rising star is, of course, Professor Kunal Kachia, who is the chair.
Yes. I think he came to Pune, Kunal.
Yeah.
Sir, madam.
I have seen his paper. He is very.
Yeah.
Madam, I was in SERB school. So
Yeah.
you taught us the nutritive method there.
Yes.
Then I hope
And where is
the
Dilip
paper.
Kumar? Dilip Kumar is missing.
Yes,
He's also
he is there.
here.
Yeah.
I think
Is
he's
Dilip
there.
Kumar there?
I am here, madam. I am here.
Yes. So Dilip is from Mathai school. I mean, so where is Professor Mathai actually?
He is currently in Thrissur now.
Thrissur. Okay.
Yeah, in Kerala itself. He will be here up to, in India, he will be up to March, he will be here.
Because Professor Mathai gave me a lot of encouragement.
Yes.
Because at that time, this fractional calculus was underestimated and people used to sort of, fractional calculus, they used to scoff at. And they did not think that it has so much of potential. Professor Mathai and his active group and all those, Professor Menardi, Gorenflo, all their visits to Kerala, and then Professor Mathai asked me to deliver lectures in Serb school. So it was a kind of encouragement to me, and that was a...
And Kiribati also visited once here.
Who?
We have Kiribati.
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 He has a book also.
Yeah. Kiribati
Yes.
was a great person. So
Yeah.
unfortunately, so many...
Yeah, we lost him in 2010. We lost him due to some accident.
We lost him, yes.
Yeah.
But now one can see those after now 25 years or maybe less, we see the fruits of all these efforts.
Yes.
In India now we are sizable work is being done. So,
Ma'am, Varsha, I could remember that workshop which you have conducted in 2009.
Yeah.
But it was a very
we started
useful one.
focusing. That was in India.
Yes.
That time people used to have only one symposium or even 2-3 lectures. But full-fledged conferences on fractional and related areas, they were not there. So now the scope of the subject also has increased manifold. In physics also now there is so much work is being done, and there is relations to statistical mechanics, and then various. I mean, you can see everywhere there is a derivative. You will have now fractional derivative. That confidence now people are gaining. So it's a good sign. Keep it up. Yeah.
Actually, there is a close connection with the statistical mechanics as well, with the fractional order. Means if we can give a proper interpretation for the fractional order with in terms of statistical mechanics, we can rewrite whole the theory of statistical mechanics in terms of fractional calculus. But it will lead to a more clear picture of what we are dealing with.
Yeah.
If we can interpret this in terms of fractional.
That's what physical interpretations are, all through statistics, basically probabilistic interpretation, because as Professor Das is saying, it is all stochastic. So once stochastic means related to statistics. That is the promising direction. And Professor Mathai is from statistics, so you can see that he has brought out all those close connections and interpretations and special functions and its relations. So mathematics gets actually very neatly tied up when you go to statistics. So it must be having a lot of now another direction is this zeros of Mittag-Leffler function. I think those things now one should take up seriously, because there we see strange dynamics and maybe deterministic dynamics. If we can get some very interesting things, fractional flow and all those things, if one can modify, so that will be another great leap into this direction. So we will find many more applications and many more situations, and let us see how it develops.
In fact, Professor Vashaman, you may be knowing Hobold. Hobold, you may be heard
Hobold,
about.
yes, yes.
Yeah, Hobold always asks a question, what is the connection between this, there is a statistical mechanics called non-extensive statistical mechanics. So, in that non-extensive statistical mechanics, there is a parameter Q. So, if this non-extensive statistical parameter Q can be connected to this fractional order alpha, then we have proper physical interpretations. So that is what he was always asking. All the time he was telling to develop a theory so that we can have proper interpretation for this fractional order. So if we can succeed in that, the main drawback of this thing when we connect it to physical systems is that we have to give a unique proper interpretation for all the situations, which is applicable for all the situations. But we fail in that. Usually when we give an interpretation, we usually give it in particular situation only. We cannot give the same interpretation for the other physical systems. So if we can succeed in that, then it will be a useful kind of.
Actually, we should have close interaction with statisticians. I mean, there is a Velayasamy in
Yes, yes.
Bombay and his collaborators. So incidentally, in one of the conferences, they looked at our Adomian decomposition method. And in one of the recent papers, Professor Velayasamy, along with his collaborators, has given interpretation of Adomian polynomials, interpretation in terms of statistical distributions.
Okay.
So that was a wonderful kind of connection. And, you know, this is the way if we interact, that statisticians like Professor Vishwesh Vyavahare, he has brought all engineering aspect, teacher, statisticians, physicists should also, I mean, surface somewhere. So fractals and these our local fractional derivatives, the way we got interested. So all those things have related to physics actually. So once that consortium develops all these, this is a very interdisciplinary area, fractional calculus and fractional differential equations. So more inputs in more directions, moment they come. So that will be a great kind of, so this is for a future plan actually. So, well, I will reserve these my comments in the afternoon. I have to talk in the valedictory function. So, okay, thank you. Thank you very much.
So at 3:40, na valedictory?
Yeah, yeah.
Yes.
Okay.
So I think now no more question or any question. So I think no more questions. So thank you so much, sir, for a wonderful talk.
Thank you all.
So you have discussed about fractional diffusion equation, fractional order ED for contaminate the transporting groundwater problem.
Yes,
and the most important part of your talk is stochastical interpretation of fractional derivative.
Correct, sir.
And the later is fractional order advection diffusion equation. And there are some open problems in that direction. So such a wonderful talk, sir. We are really fortunate to listen you in the even virtual mode. So thank you so much, sir.
Thank you. Thank you very much. Thank you. Thank you very
Sachin,
much.
sir, for giving this opportunity to session the chair. Now it's over to you.
Thank you. Thank you, Dr. Krunal, for chairing this session. Thank you, Dr. Subir Das, for a nice talk.
Thank you, sir.
I'm very happy that there is nice discussion. I'm thankful to Varsha Gidji ma'am, Professor Ram James Devan, Vishwesh Vyavahare sir, Krunal Kachia, Santanu Sahare sir, Dilip Kumar, and other eminent persons. So, Gidji ma'am organized such workshops long back, and she motivated us to organize such programs. Somehow I was unable to organize conference before this, but now in online mode, things are quite simpler. So I tried to organize. Thank you one and all. In the morning session, we covered the applied mathematics topics. We organized some talks on theory as well as applications. In the post lunch session, there will be two talks. One is by Dr. Kishore Kusai from Shivaji University, Kolhapur, and another will be by myself. So
Okay.
thank you. I declare this session. We will meet at 1:30.
Okay, sir.
I request participants to be here for some announcements. Thank you.
Thank you, sir. Thank you.
Dear participants, we will have valedictory session at 3:40 p.m. I already shared the invitation to your registered email addresses. I expect some of the participants should give feedback in that session. So please give me some names. So it will be 2 to 3 minutes talk. It will be informal. So please, who will? I expect some participants from other countries. Ahmad Haji Zadeh. Sir, can you share your feedback in the valedictory session? Ahmad Haji. Can you unmute, please? Dr. Satish Kumar. Gunan Birazdar, sir. Gunan Birazdar.
Yes, sir. Yes, please.
Would you like to share your views in valedictory session?
Yeah. Yes, sir. Yes, please. Thank you, sir.
Thank you.
Thank you so much.
Then let's see. Any other participant? Yogeshwari Patel. Wahid Hussaini.
Yes, sir.
Yes. Will you be able to share your views?
Yeah.
Sorry.
Yeah, we can do.
Yes. Thank you. It will be 2 to 3 minute talk about your views, your experience.
Sure, no problem.
Okay, thank you. Anyone? Revati Zayam. Nora. Mohammad Iqbal Khan. Manita Bhaktani. Manita ma'am, will you be able to share your views? Madhukar Zanje.
Yes, sure, sir. Why not, sir? I'm ready.
Thank you, sir. Gauri Morai. Are you there? Dr. Satish Kumar. Dr. Satish Kumar, are you there? Yogeshwari Patel raised hand. Yes, you are ready. Thank you. Yes, yes. I read that. Anyone from outside India? I can see some participants like Ahmad Hazi. Chetna Biswas. Dr. Smita Nigam.
Sir, Azizul Islam raised his hands, no? Azizul Islam.
Azizul Islam. Can you unmute? Do you want to say anything? Or please write in chat box. Azizul.
Okay, sir. Yes, sir. I will write in my
I
chat.
can hear you. Please.
I can say that organize such type of conferences and events more and more and inform us so that we can.
Not now. In the valedictory session, do you want to share your experience?
Okay, sir. I will write in my chat box.
I mean, not now. It is at 3:40 p.m. in the valedictory session.
Okay, sir.
Okay. Thank you. So thank you all. We will meet at 1:30.
Okay.
There is lunch. Thank you.
Thank you very much.
simple.
audible? Am I audible?
Yeah, hello, sir. Yeah.
Just wait, sir. Hello, sir. Hello.
Hello. So, welcome back in this post-lunch session. I invite Dr. Barney Balan from Central University of Tamil Nadu to chair this session.
Yeah, thank you, sir. Can you hear me voice?
Yes, yes.
Yeah. Good afternoon to all of you. So I welcome everyone for the second day afternoon session of International Conference on Fractional Calculus. So the resource person for this session is Professor Kishore Kuche. He is from Shivaji University, Kolhapur, Maharashtra. He has more than 18 years of teaching experience. His area of interest, fractional differential equation, abstract differential equation, integral inequalities, dynamic equation on time scales. So he has published more than 40 research papers in a well-reputed international journals with good citation and H-index and Titan index. So, and his research collaboration in various places like Brazil, Spain, China, and Saudi Arabia. So under his guidance, 3 candidates completed their PhD courses, and one person is pursuing PhD. So he completed one UGC minor research project, and the one project is currently running under SCRB. And he visited USA, and he organized several conferences and workshops sponsored by CSIR, SCRB, and UGC DST. And he was part of the various academic and research and administrative committees. So with a short note, I welcome Professor Kishore Kuche to talk on calculus of generalized Hilbert fractional derivative. Welcome you, sir.
Thank you very much, Professor Barani, sir, for the introduction. Thank you very much. I'll share my screen. Just a moment. Can you see my screen, sir?
Yes, sir. Yes.
Okay. Am I audible, sir? Properly?
Yes, sir. Yes.
Okay. Thank you. Good afternoon, one and all. Thank you very much again. I will talk on generalized Hilbert fractional derivative and nonlinear fractional differential equation involving generalized fractional derivative. The outline of talk is briefly related to the fractional calculus, necessity of generalized fractional derivative. Then we'll discuss concept of fractional derivative with respect to another function. Then we'll discuss generalized Hilbert derivative called psi-Hilbert derivative, and fractional differential equation involving psi-Hilbert derivative. We will study existence, uniqueness, and data dependence result for psi-Hilbert differential equation, and then we'll go for conclusion. This presentation is based on these 2 research papers. This is well known to that fractional calculus is the branch of mathematics that deals with integral and derivative of arbitrary order called fractional derivative and fractional integral, which generalizes nth order differentiation and n-fold integration. We know this famous conversation between Newton and Leibniz. Leibniz introduced this symbol of nth order derivative and communicated to L'Hopital, and L'Hopital replied what happened when n is equal to half, and it is the start. This is considered as the start of fractional calculus. If we observe the literature related to the fractional derivatives and fractional differential equations, we can see number of definitions are there for the fractional derivatives. till now, till today, we can see that more than 30 to 33 definitions are there for the fractional derivative that are available in literature. And these definitions, which are available in literature, do not coincide in general. Possibility it is due to the fact that different authors try to preserve the different properties of the classical integer order derivative. Generally, new fractional derivative is proposed with the two aims. One is existing fractional derivative doesn't fulfill the properties of the classical ordinary derivative, or when one cannot demonstrate some physical process with the existing fractional derivative. Okay, so these are the two aims. Generally, we are trying to propose new fractional derivatives. These are the few definitions I have mentioned here. Of course, this is not the exhaustive list related to classical fractional derivative, which include Grunwald-Litnikov derivative, Sonon-Litnikov derivative, Liouville derivative, up to Edley-Colbert derivative. This is, of course, not exhaustive list, and new fractional derivatives in the last decade have been proposed by that is Machado derivative, Chen-Machado derivative in 2015 and 16. To remove the singularities in the fractional derivatives. Okay, Caputo and Fabrizio has proposed one derivative involving exponential function, and Atangana, Bellino, and Caputo proposed in 2016 a fractional derivative involving Mittag-Leffler function as a kernel. Okay, and in 2018, Souza and Oliveira proposed a psi-Hilbert derivative, which is generalization of the Hilbert derivative. Okay. Now, whenever derivative is proposed, fractional derivative is proposed, it is expected that it must be a natural generalization of your classical nth order derivative, natural order derivative. Okay, these are the properties, 1 to 7 are the properties of the classical derivative, which we are expecting that must be satisfied by fractional derivatives also. Suppose alpha is real number, positive real number, and delta is operator. Fractional derivative operator, some fractional derivative operator. If alpha we are taking natural number, okay, it must give your classical derivative. This must give classical derivative means backward compatibility is expected from your proposed derivative. It must give zeroth order derivative must give function as it is. Means zeroth order operator, fractional derivative operator must act as an identity. Linearity property must be satisfied by that fractional derivative. Commutativity should be there. Index loss should be there. We must be able to provide Leibniz formula for the product rule in the form of fractional derivative, and composition, derivative of composition must be there for that fractional derivative. Unfortunately, if you observe the literature of any fractional derivative, none of the fractional derivatives satisfies this all property in generally. And already I have explained, already I have talked that there are many definitions of fractional derivatives. Out of that, most widely used definitions in literature we can find out that are Riemann-Liouville derivative and Caputo derivative. Why these derivatives are most popular? Because we know a Riemann-Liouville fractional derivative plays an important role, mainly in the development of theory of fractional derivatives for application in pure mathematics, and applied problem requires proper definition of fractional derivative, which can provide initial condition with clear physical interpretation. That is not happen in the case of Riemann-Liouville fractional derivative. We know that when we are taking the Laplace transform of Riemann-Liouville derivative, or when we are considering integration of derivative of Riemann-Liouville derivative, initial conditions are generated in the form of fractional derivative and fractional integral. Okay, that is not the case for the fractional derivative. Okay, so in the view of applied problem, Caputo fractional derivative is more suitable, and a lot of paper we can find out with these two fractional derivative. This is the definition of Riemann-Liouville fractional integral. Okay, suppose alpha is positive real number, non-negative real number, alpha greater than or equal to 0, then alpha order integration of f of x is defined by this way, where this gamma is Euler gamma function, and 0th order integration of f of x, we are defining f of x. It has a reason, because when we are taking the limit of this fractional integral as alpha tending to 0, it gives f of x. So it is justifiable to put that 0th order integration of f of x is equal to f of x. For detailed proof related to its limit as alpha tending to 0 is equal to f of x, we can find out in book of Podlomny. Having known a Riemann-Liouville fractional integral, the Riemann-Liouville fractional derivative of order alpha for the function is defined in this way. It's a classical nth order derivative of n minus alpha fractional integral of f of x. This is the elaborated form of fractional derivative, Riemann-Liouville fractional derivative. When we are taking alpha is equal to n, this operator become identity operator. So f of x remain as it is here, and we are getting classical derivative. Okay, so we can think that Riemann-Liouville fractional derivative is the natural generalization of your classical nth order derivative. Similar is the case for your Caputo derivative. This Caputo derivative is what your n minus alpha order fractional integral of classical nth order derivative. This is again elaborated form of it. Now, necessity of generalized fractional derivative. As already I have discussed, there are a number of definitions related to fractional derivatives and fractional integral. And over time, new fractional derivatives and fractional integral will rise. That's why it is necessary to introduce a derivative operator that unify wide class of fractional derivative. Okay. What is the importance of it? Introducing generalized fractional derivative operator will overcome a number of definitions related to your fractional derivatives. And with generalized fractional derivative, we can study the existence and different type of properties of solution under one roof with generalized fractional derivative. That is the aim for defining generalized fractional derivative. The first attempt toward the generalization of fractional derivative has been made by the mathematician Hilbert in 2000, who introduced fractional derivative of two parameters when alpha is a real number between, say, two consecutive natural number n minus 1 to n, and beta is in the closed interval 0 to 1. Then this two parameter operator, fractional derivative operator, is defined in this way. It's a Riemann-Liouville integral of order beta into n minus alpha of n time operated d by dx on this fractional integral of order 1 minus beta into n minus alpha of f of x. Of course, these two are Riemann-Liouville fractional integral. One can observe that when I will take beta is equal to 0, this definition is reduces to Riemann-Liouville derivative. And when we will take beta is equal to 1, this definition reduces to Caputo derivative that is specified here. Okay, so when we can see that this Hilbert derivative definition interpolated between Riemann-Liouville derivative and Caputo derivative. Then the concept related to fractional derivative of the function with respect to another function, just like your Riemann-Stieltjes integration of the function with respect to another function, because we know fractional derivative maybe it may be your Riemann-Liouville say or Caputo say it is defined in the form of fractional integration. So we can expect the integration of the function with respect to another function, and since fractional derivatives are defined in the form of integration, we can think of the fractional derivative of the function with respect to another function. The concept of fractional derivative of the function f with respect to another function, say psi, in the sense of Riemann-Liouville can be found in this monograph by Kilbas and ATL, Kilbas and other. We call this derivative as psi Riemann-Liouville fractional derivative. On this line, Almeida in 2017 introduced concept of fractional derivative of the function with respect to another function psi in the sense of Caputo derivative. And most generalized version, this is generalized version in the sense of Hilbert, considered by Souza and Oliveira, and they introduced a psi-Hilbert fractional derivative, and in that paper they have proved that psi-Hilbert derivative incorporates many well-known fractional derivative as its particular cases. This is the concept of Riemann-Liouville integration of the function f with respect to another function psi. Okay, we are calling this psi Riemann-Liouville fractional integral. Okay. So if alpha is a positive real number, psi is increasing and positive monotone function defined on interval, and its derivative is non-vanishing on this interval. Okay, then fractional integral of this function is 1 upon gamma alpha a to x. This is the formula for it. One can check that if you are taking in particular psi t is equal to t, identity psi t is identity function, then this definition is converted in the form of what yours Riemann-Liouville fractional integral, classical definition of Riemann-Liouville fractional integral. Okay, so that is specified here. Suppose if you are taking psi x is equal to x, identity function, then your psi Riemann-Liouville fractional integral is converted in the form of Riemann-Liouville integral, fractional integral. If you are taking psi x is equal to x, a is equal to minus infinity, this gives your Liouville fractional integral. If psi x is equal to log x, Okay, we are getting here psi Riemann-Levy integral converted to Hadamard fractional integral. If we take psi x is equal to x raised to sigma, g of x is equal to x sigma eta f of x, this combination, this operator gives your Edley-Cover fractional integral. If you are taking psi x is equal to x, gx is equal to x raised to eta f of x, and a is equal to 0, this operator gives your Cobell fractional integral. If you are taking psi x is equal to x rho, okay, this operator gives Cartan-Poloff fractional integral. And if we choose psi x is equal to x, gx is this term in the form of generalized two-parameter Mittag-Leffler function, then this operator operated on g of x gives Prabhakar fractional integral. Of course, this is, as I already had told you, this is not the exhaustive list. Okay, so I am specifying here some few important cases only. If you are taking psi x is equal to x, a is equal to minus infinity, b is equal to infinity, this linear combination gives you a Riesz fractional integral. Okay, so this single concept, psi Riemann-Levy fractional integral, incorporate many concepts, many fractional integral defined by different authors, different mathematicians. Okay, so say this is our power function in the form of say psi, del is positive, alpha is positive, fractional integral is available for it. Fractional integral for the power function is given in this format. We can obtain the fractional integral for trigonometry function, sine, cos, and other trigonometry function, logarithm function using this formula, because we know that sine, cos, and other trigonometry function and your logarithm function has a convergent power series expansion. Okay, so using this formula, we can obtain fractional integral of that function also. This is the concept of psi Riemann-Levy fractional derivative introduced in the book of Kilbas and other. This definition is given in the sense of Riemann-Levy fractional derivative, Riemann-Levy derivative with respect to another function, we can say. Okay, so it is defined in this way. Psi we are considering here continuously differential function, increasing, and it is non-vanishing on this interval. Okay, then psi Riemann-Levy derivative is defined by n time operator operated on this n minus alpha order psi Riemann-Levy integral. So this is 1 upon psi dash d by dt. Since psi dash is appearing in denominator, we require it is non-vanishing function. On this line, as already I have discussed, Almeida introduced this concept of psi Caputo fractional derivative, which is n minus alpha order psi Riemann-Levy fractional integral operated over this operator, n time operator 1 upon psi dash t d by dt over f of t. Again, we have the formula for the power function in the form of Riemann-Levy derivative, psi Riemann-Levy derivative. This is the relation between psi Riemann-Levy derivative and psi Caputo derivative. Okay, this is the f bracket k psi. This is the operator defined in this way. It's a k time operator operated on f of x. This operator is 1 upon psi dash x d by dx. And we can see that if I am taking here psi x as identity function, psi of x is equal to x, this result includes the result of result proved in the book of Kai Dithel. That is relation between Caputo derivative and Riemann-Levy derivative. This is the definition of psi Hilbert fractional derivative, which can be regarded as a generalized version of Hilbert derivative. Okay, this Hilbert derivative of the function with respect to another function. Okay, we are calling this as a psi Hilbert fractional derivative. Again, we are considering here f and psi are n time continuously differential function. Psi is non-vanishing on this interval I. Okay, and alpha is positive. We will suppose that it is between two consecutive natural number n minus 1 to n. Okay, then psi Hilbert derivative of order alpha and type beta. Okay, where beta is between 0 to 1 of this function is defined in this way. Okay, so it is a fractional integral of order beta into n minus alpha order operated on this operator of this psi Riemann-Levy integral of order 1 minus beta into n minus alpha. The Psi-Hilbert derivative is expressed in this form of Psi-Riemann-Leibel integral of Psi-Riemann-Leibel fractional derivative. Okay, Hilbert derivative, Psi-Hilbert derivative, we can express integration of Psi-Riemann-Leibel derivative, where gamma is what? Alpha plus beta minus alpha beta. This formula is important when we deal with the fractional derivative, fractional differential equation involving Psi-Hilbert fractional derivative to obtain its equivalent fractional integral equation, or to obtain the formula for integration of fractional integral of this Hilbert derivative. Okay, so at that time this formula is needed. Okay, that's why this formula is important. Again, we have the derivative of this power function in this format. Okay. If we consider f of x in this form of Mittag-Leffler function, one parameter Mittag-Leffler function, E alpha of lambda psi x minus psi a raised to alpha. Psi already we have specified, lambda is some positive real number. Then it satisfies this linear fractional derivative differential equation involving Psi-Hilbert derivative. Okay. As already I have mentioned that Psi-Hilbert derivative includes wide class of fractional derivative. By choosing different values of parameter beta and different function psi, we will get different fractional derivative. This is the list we have provided here. If you are taking, this is say my Psi-Hilbert derivative operator. If psi t is as it is, alpha as it is, and if I are taking beta is equal to 0, we are getting here Psi-Riemann-Leibel fractional derivative as particular case of Psi-Hilbert derivative. If psi t as it is, alpha as it is, beta is equal to 1, then this Psi-Hilbert derivative reduces to your Psi-Caputo derivative. If psi t is equal to t and beta is equal to 0, then it reduces to Riemann-Leibel derivative. If psi t is t and beta is equal to 1, it reduces to Caputo derivative. These are the functions we have specified by here psi t, and values of beta here we are obtaining as a particular case Catung-Pula derivative, Caputo-Catung-Pula derivative, Hilbert-Catung-Pula derivative, Hadamard derivative, Caputo derivative, and other derivatives are specified in this paper. Okay, so again I am specifying that this is not exhaustive list. Okay, so that's why this derivative we are considering is a generalized derivative which incorporate all these derivative. Now we will consider Psi-Hilbert fractional differential equation. Okay, so we consider non-linear Psi-Hilbert fractional differential equation of this format. Okay, which is if you are taking which is generalization of your basic Cauchy problem, y dash is equal to f t y, y at a is equal to y at a. Okay, so here gamma we are taking alpha plus beta into 1 minus alpha. This is Psi-Riemann-Leibel integral of order 1 minus gamma, and this is the nonlinear differential equation, initial value problem for nonlinear differential equation involving Psi-Hilbert derivative. Considering this nonlinear differential equation, initial value from nonlinear differential equation, we have investigated existence, interval of existence, and influence resultant in the weighted space of the functions. And data dependency results we have investigated through Weisinger fixed point theorem. We have developed Picard successive approximation method and proved that this Picard successive approximation approximations sequence related to Picard successive approximation converges to the unique solution of this nonlinear fractional differential equation. And estimation estimation obtained for the error bound, that is bound for difference between approximated solution and exact solution, have been obtained in the weighted norm. Okay, so to consider the solution of fractional differential equation involving Psi-Hilbert derivative, we require a generalized space. Okay, so we introduce here the space of weighted function. Okay, that is defined here. Okay, where suppose gamma is between 0 to 1, including your value 1. Okay, then C suffix 1 minus gamma psi AB is the space of all functions such that this weight psi t minus psi raised to 1 minus gamma f of t is continuous for each t with this weighted norm. And these two spaces we require to develop free properties of means to develop the calculus of fractional Hilbert fractional derivative. Okay, so we will obtain the solution of the differential equation in this space. Okay, we can see that when we are taking gamma is equal to 1 here, this space is converted in the form of what your space of continuous function, CAB. Okay, space of all continuous function defined on closed interval AB. We will get, okay. Because psi-Hilbert derivative is considered as, it is generalization of many fractional derivative, okay. So whenever we are considering fractional differential equation involving different type of derivatives, okay, according to that, the solution space we have to consider, okay. So this is the generalized space is constructed, okay, which we consider as a solution space for the fractional differential equation involving your psi-Hilbert derivative. Okay, so this is the first result related to existence and interval of existence. Okay, let gamma is this alpha plus beta into 1 minus alpha, where alpha is the order of derivative and beta is between 0 to 1. This is the rectangle defined where this function yet psi gamma is this psi t minus psi raised to gamma minus 1 upon gamma of small gamma. Yep, we are considering continuous on this R naught. And we will assume that for each y in the weighted space, okay, this function yep is in this weighted space, okay. And psi, we are assuming that increasing bijective function, which is non-vanishing for on this interval. Then this initial value problem possesses at least one solution in this weighted space. And this is the interval of existence, A to A plus chi, where chi is minimum of psi and this quantity. Okay, so we have checked that this quantity is exist because psi is increasing and bijective. Okay, for proving the existence result, we have used Schroeder fixed point theorem, and we have proved existence theorem through this equivalent fractional integral equation, which is proved in 6. Okay. So in the view of this fractional integral equation, we have defined this operator A on this set U. Okay, so this U set is a subset of this weighted space, and one can see that this is a closed, convex, and bounded set. Okay, and we prove that with the help of this operator, okay, we can see that this fractional equivalent integral equation can be written as an operator equation, y is equal to ay. Okay, thus the fixed point of this A will act as the solution of nonlinear initial value problem. Okay, so we'll prove that this A has a fixed point using this Schroeder fixed point theorem. So we will prove that A satisfies the assumption of this Schroeder fixed point theorem. We have to prove that A is relatively compact operator. Okay, so first we prove that A maps sets U to itself, then operator A is continuous on U, AU is uniformly bounded subset of this. Okay, so detailed proof I have omitted here, and lastly we'll prove that this set A of U is equicontinuous. And in the view of Pascual-Arzola theorem, we can say that A is relatively compact and A is my compact operator. Okay, so in the view of Schroeder fixed point theorem, we say that A has a fixed point in this weighted space, which acts as a solution of the initial value problem, which we have considered. This is the existence result. Okay, so all the assumptions of uniqueness theorem. This is uniqueness theorem. All the assumptions of existence theorem we have considered. In addition to that, we have imposed this condition, Lipschitz condition on it to prove the uniqueness. Okay. And again, we have proved existence as well as uniqueness in this weighted space. Okay, and this is the interval of existence where chi is defined in this way. Okay, this is the Weisinger fixed point theorem. We have to define the operator A from U to U, where U is non-empty complete metric space. And the operator Aj must satisfy this contraction condition in which this alpha j, the summation from this alpha j must be convergent. Then we can say that A has a fixed point in U, fixed point. And if you are taking any point in this say space U, then the sequence Aj U naught from j is equal to 1 to infinity, this converges to your U star. Okay, so these two things we require to prove existence as well as uniqueness of the solution for the initial value problem which we have considered. Okay, so we continue with the same operator which we have considered in existence theorem. Okay, And we have proved by mathematical induction, okay, that for any natural number 1, this operator an satisfies this inequality, any minus a raised to nz satisfies this inequality. Okay, of course, all the calculation have been done with respect to this norm, weighted norm. Okay, and if you consider this term that we will call alpha n, which is the nth term of 2-parameter Metagliffer function. And since this series is convergent, using Weisinger fixed point theorem, we can say that it has a unique solution in this weighted space. Here, this theorem is related with continuous dependent of solution on initial condition. Again, all the conditions are same as in existence and uniqueness theorem. Okay, and we are considering 2 initial value problem. One in equation number 10 with the initial condition, say y suffix a, and another this differential equation is same. Okay, means nonlinear function f is same. Just we have varied here initial condition. Okay, then the solution y of the initial value problem and solution z of the initial value problem L11 the difference of these two in the with respect to weighted norm satisfy this inequality. Okay, here is the norm of y a tilde minus z a tilde, where y tilde and z a tilde are the functions defined by this way. Okay, so this y a tilde and z a tilde, these are the function depend on this y a and z a. Okay, and we can see that this y a tilde and z a tilde are the member of this set U, which we have already defined in the last set. Okay, here member of this set. Okay, so we can apply Weisinger theorem. So these 2 sequences have been considered in the form of a raised to m y a tilde and am z a tilde. So am y tilde defined by 14 and 15, and am z a tilde, this sequence is defined in this way. Again, by using mathematical induction. Okay, this we have proved am y a tilde minus am z a tilde, difference of these two with respect to this norm satisfy this inequality. Okay, and when we take limit as m tending to infinity and x tending to chi, this inequality reduces in this format. Okay, so we are getting here dependence of solution y and z on the initial condition. Okay, where y tilde involve ya and z tilde involve your z, the initial condition related to the problem 10 and 11. Okay, and if our initial condition y and z are same, the function y tilde and z tilde become same. So this data dependence result gives uniqueness also when we have the initial condition same. Okay, the existence result is proved through Picard successive type approximation also. So firstly we'll deal with non-linear case. Okay, for that we require this theorem firstly. Okay, so again gamma, alpha, beta, this rectangle, f, psi are as in, and this chi are as in the as considered in your existence and uniqueness theorem, and m is the bound of this quantity. Okay, so f into psi t minus psi raised to 1 minus gamma less than or equal to m. This m exists because of we are considering here this f is the member of weighted space whenever y is the member of weighted space. That's why this m is exist. If we define the successive approximation, Picard type successive approximation in this way, y naught t is equal to psi t minus psi raised to gamma minus 1 upon gamma of gamma into y of a, and motivated by equivalent integral equation, yn defined in this sense, then each yn is the member of weighted space for all the values of n 0, 1, 2. Okay, and this weighted difference yn minus y naught with this weight is less than or equal to this quantity. This theorem we need to prove the convergence of Picard successive approximation. Okay, this successive sequence, this successive approximation converges to the solution of initial value problem. To prove that, this theorem is needed. So these are the conditions which we have considered again in existence and uniqueness theorem. Alpha, gamma, beta, f, we are taking same as we have considered in existence and uniqueness theorem. And in addition to that, we are assuming here f satisfies the ellipsis condition in second argument. Then the Picard successive approximation defined in this way converges to the unique solution y to the of the Cauchy problem 1, 2 in this weighted space. This we have proved. Okay. So having proved convergence of successive approximation in the nonlinear case, we can apply it for the linear case directly. Okay. So using Picard successive approximation, we are able to provide the explicit representation formula for the solution of linear problem for constant coefficient. Okay, non-homogeneous linear problem with constant coefficient. Okay, and its solution we have obtained in the form of two-parameter Metaglifleur function, and for linear differential equation involving psi-Hilbert derivative of homogeneous type, we have obtained the solution in the form of Metaglifleur function, a generalized Metaglifleur function defined by Sayago and Kilbas. Okay, so we will assume that we will consider this non-linear psi-Hilbert differential equation. Okay, 24 and 25. This f function, we will assume that in the weighted space. Okay, then its solution is given by this way. Okay, and this solution is obtained using Picard successive approximation. Okay, so we have proved its convergence. Okay, so that's why using that theorem, we can apply Picard successive approximation to obtain the solution of this linear problem 24 and 25, and we have obtained this solution. Okay, one can easily check that if you are taking psi t is equal to t and beta is equal to 1, this problem is reduces to what your Caputo derivative, and we will get the representation formula in the form of what Caputo derivative. Okay, which we can see in literature. Similarly, here we have considered homogeneous linear differential equation with variable coefficient. So f is in weighted space, lambda is real number, mu is greater than 1 minus alpha. Under this condition, we have proved that this linear problem 27 and 28 has solution in the form of generalized Metaglifleur function defined by Kilbas and Sayago. This is a 3-parameter Metaglifleur function. Okay, conclusion. The importance of psi-Hilbert fractional derivatives lies in the fact that it includes a number of well-known fractional derivative operators. Its particular cases include a well-known fractional derivative Riemann-Leibniz and Caputo derivative. Okay, so whatever the theory which we are studying for related to existence, uniqueness, stabilities, for the differential equation involving different type of derivative, okay, that can be obtained under one roof by considering psi-Hilbert derivative. Okay, these are the references related to this presentation. Okay, and just I will introduce one concept and then I'll stop. Motivated by this concept of psi-Hilbert derivative, okay, we have extended concept of psi-Hilbert derivative to the case psi-Hilbert fractional derivative. The motivation for this work is published in the journal Chaos, Solitons and Fractal recently in 2021. Okay, so we have developed a theory related to case psi-Hilbert fractional differential equation, case psi-Hilbert fractional derivative, and studied fractional differential equation involving case psi-Hilbert derivative. Okay, in 2007, Diaz and Pariguan introduced this definition of K gamma function. Okay, we can observe that this is generalization of your Euler gamma function. Okay, when we are taking K is 1, this K gamma function converted in the form of what your Euler gamma function. Okay, since K gamma function is the natural generalization of gamma function, and we have seen that several definitions of fractional derivatives and fractional integral depend upon your Euler gamma function. So it is natural to expect the fractional derivative with additional parameter K. Okay, motivated by this fact, okay, we have considered generalized version of Psi-Hilbert derivative. That is what we call K Psi-Hilbert derivative. Okay, so this is your definition of K gamma function. It satisfies functional equation similar to Euler gamma function. Gamma K of K is equal to 1, and this is the relation between gamma K function and usual gamma function. Similarly, there is concept of beta K function. Okay, this is relation between beta K function and beta function. Okay. These are the few definitions related to what your K Riemann-Leibniz fractional integral. Okay, so my motivated by this fact, we have introduced this concept. Okay, so when alpha is between two consecutive natural number m minus 1 to m, h and psi are n time continuously differentiable function, then the Psi-Hilbert derivative, K Psi-Hilbert derivative of this function. Okay, sorry, this is the definition of Psi-Hilbert derivative which we have just discussed. Okay, this is the definition we have introduced. Okay, in the paper which I have shown just. Okay, so when alpha and k are the real number in this interval 0 to infinity, beta is between 0 to 1, psi is m time continuously differentiable function, and h is m time continuously differentiable function, then this K Psi-Hilbert derivative of the function h of order alpha and beta is defined in this sense, in this way. Okay, so this is a K Psi Riemann-Leibniz fractional integral. Okay, and m we are taking the ceiling of alpha by k. Now it is observed that when we are taking beta is equal to 0, K Psi-Hilbert derivative reduces to K Psi Riemann-Leibniz fractional integral. If you are taking psi t is equal to t in this definition, it is reduces to K RL fractional derivative. And if you are taking K is equal to 1, K RL fractional derivative reduces to your RL derivative. Okay. For beta equal to 1, K Psi fractional derivative reduces to K Psi Caputo derivative. Okay. And for beta is equal to 0, K Psi fractional derivative reduces to what your K Psi Riemann-Leibniz fractional derivative that already I have explained. Okay, so we have got this K Psi Riemann-Leibniz derivative and K Psi Caputo derivative as a particular case of this K Psi-Hilbert fractional derivative. Okay, and few definitions which are defined in the literature. We have proved that it is observed that K Hilbert fractional derivative defined in reference number 9 does not include definition of K RL derivative, but the formula which we have defined for the K Psi-Hilbert derivative, okay, when we are taking psi t is equal to 1, it reduces to your K Psi-Hilbert fractional derivative, and it includes the definition of K RL fractional derivative as a particular case if you are taking beta is equal to 0. Okay. So whatever the theory we require to develop the calculus of K Psi-Hilbert derivative, that theory we have developed for K Psi Riemann-Leibniz fractional integral. So these are the few results which I have specified here. So it is not possible to read all because of the time constraint. Okay. And we have developed here properties of calculus of K Psi-Hilbert fractional derivative also. And this problem you have considered involving K Psi-Hilbert fractional derivative and existence and uniqueness result we have proved this in this generalized case. Okay. So when we take K is equal to 1, of course it is converted in the form of gamma. Gamma lies between 0 to 1. So we are getting again the weighted space which we have considered in the case of Psi-Hilbert derivative. Okay. And this is the weighted norm which we are considering, generalized weighted norm. Okay, and existence and uniqueness result we have proved here. Okay, so we have given the equivalent fractional integral equation for this non-linear fractional differential equation in 5 and 6. Okay, so a lot of calculation is required to do this. Okay, because right, and this is the existence result we have proved, assuming the Lipschitz condition on F, and F is the member of this weighted space. So this is the conclusion related to this K Psi-Hilbert derivative. Okay, so we introduced most generalized variant of Psi-Hilbert derivative, namely K Psi-Hilbert fractional derivative, and proved few of its property. Many other properties of K Psi-Hilbert fractional derivative are open for the investigation. For K is equal to 1, K Psi-Hilbert fractional derivative reduces to Psi-Hilbert derivative, whose property is studied in 6. For psi t is equal to 2 and K is equal to 1, this K Psi-Hilbert derivative reduces to your Hilbert derivative. Okay, and these are the particular cases which we have specified here. Okay, these are the this is the table. Again, I am this is not the exhaustive list related to the particular cases of K-psi helper derivative. These are the particular cases when K is greater than 0 and when K is equal to 1, this derivative reduces in this format. Okay, so this is most generalized version of K-psi helper derivative. These are the references. Thank you.
Yeah, thank you, sir. So now the session open for audience.
Interesting talk by Dr. Kuche.
Thank you very much, madam. My almost all work is motivated by your work, ma'am. I am again one of the student in Maharashtra, which is motivated by your work and Bhalekar's work, madam.
Yeah.
So already that
So
professor,
it is quite
he told
interesting. Yeah, sure. So what is the advantage? I mean, it's quite interesting to see that you can generalize gamma function by introduce one parameter. So have you ever seen any application or it's some physical interpreter or something like?
Okay.
Otherwise, I mean, audience can take it as a research topic also, like modify your
yes.
thing. And then suppose, then you consider all your, say, dynamical systems or usual systems. And
Okay,
then just see what is happening. I mean, it is interesting. Who introduced this generalization? Gamma K?
Firstly, gamma K, it is introduced by, sorry. This is Diaz and Pariguan, reference number 1, madam.
Yeah. Okay.
This I will show just, this is here. On hypergeometric function and Pochhammer K symbol.
Okay.
So we have we are extending few properties of this fractional derivative using Pochhammer K symbol also. There is one Pochhammer symbol whose generalization is there for Pochhammer K symbol. Okay. So we are working in that direction also, madam. Okay. I will come to your question, ma'am. Okay. What is the main aim for having generalized fractional derivative operator? That already I have explained, madam, because right from starting of birth of the fractional calculus, that already I have explained that there are a lot of definitions related to the fractional derivative. Okay. I have already explained that there are near about 30 to 35 definitions related to fractional derivative. Okay. And each one are studying fractional differential equation and fractional calculus by taking different derivatives.
Yeah.
Okay. So a lot of theories are there with different type of fractional derivatives. Okay. Aim of my study is that how to unify this operator under one operator. That is the main aim, madam.
Yes,
that is the main aim. Okay. With this aim, the fractional K-psi helper derivative defined in that sense only, so that it will incorporate a number of derivatives. Okay, so
most general kind of
most general kind of derivative. Okay, so it involve means it involve the function psi. That's why we cannot give its physical interpretation, madam. Just so like it is Riemann-Stieltjes integration. We cannot give the physical interpretation of Riemann-Stieltjes integration.
No. My question is right. I mean, as a pure mathematician, it is always good to generalize to the most possible extent. But also, if one looks for, I'm posing this question in more general audience, like one can look up and take up this study. That people who are doing modeling using fractional order derivatives, what will be the interpretation of this K parameter? That kind of thing. It is not, I'm particularly asking you a question. It is I'm saying ki, mathematicians always have a very general and abstract spaces and most generalities they work. But when it comes for practicalities or its utility value, so that opens up new kind of area for researchers, young researchers who want to study these or want to model phenomena using this or interpretations of this. So it is an interesting topic, I should say. Okay.
Thank you, ma'am. Thank you very much.
Good afternoon, sir.
Good afternoon, madam.
sir. Very nice presentation. I'm Ramalakshmi, research scholar. My
Thank you,
question
ma'am.
is, why should take psi is an increasing function in the definition of a psi Hilbert fractional derivative?
Madam, we some disturbance is there. Gade sir, Gade sir. Okay.
Sure, sir.
Okay. We know, madam, Riemann level integration. Sorry, what is that? Your usual Riemann integration is increasing operator. If you are taking x is less than y, then integration of x is less than integration of y. Okay. It happened for your fractional Riemann level fractional integral also. It is also an increasing operator. If you are taking x is less than y, then Riemann level fractional integral of x is less than Riemann level integral of y. Okay. To maintain that increasingness property of integration, that's why required psi is increasing function. That's why it is needed, ma'am.
Okay, sir. Thank you, sir.
Good afternoon, sir.
Hi, yes, ma'am. Please, Deepali, ma'am.
Sir, actually, I am a fresher in this field. But as we know, the fractional derivatives have good memory effect compared to the ordinary derivatives. So can you just brief me about memory effect? What is memory effect?
Okay. I will try to visualize your concept mathematically, ma'am. Okay. Suppose we are considering the classical derivative concept, f dash of t. Okay. To define f dash of t, that is in the form of limit. Limit x tending to t f of x minus f of t upon x minus t. Okay. To say that x tending to t, that t must be the limit point of your function f. Okay. So that we can say that, so that we can define the limit concept x tending to t. Okay. Are you understanding, madam? When I am speaking x tending to t, there should be some values to pass x towards t. Okay. So t must be the limit point of domain of that function that is needed. Okay. You know the definition of limit point, that is in the form of neighborhood. Okay, so to define the concept of classical derivative, your function must be known locally in some neighborhood of t. Okay, but you have observed a fractional derivative concept. It may be your say Riemann level derivative, or it may be say your Caputo derivative, or many derivative you can say, that are all defined in the form of integration, fractional integration, and the range of integration is a to t. Okay, a to t. Okay, so your function must be known in that that line a to t. Okay. So that function must be known in that span.
Yes.
Okay. So that span indicate your memory effect of that fractional derivative operator.
Okay,
It is just my mathematical answer to you. I have not checked in the sense of practical way.
Okay. Thank you, sir. I have one more small question. Hello.
Hi, yes, ma'am. Please.
We say that a Caputo derivative have singular, kernel have in Caputo derivatives, fractional derivatives, kernel have singularity. So
yes, ma'am. Yes.
So, sir, kernel means it is same. It has same meaning as we have algebra. The all points which take that function to 0. So, what is kernel meaning here?
No, madam. The kernel means that when we are considering any type of transform, now, ma'am, Laplace transform, Fourier transform, some term is there in integration. That term we are calling kernel, k of xt. Okay. So suppose we are considering Laplace transform, say Laplace of f of t, we are defining like integration 0 to infinity e raised to minus st f t. So that e raised to minus ft is we are calling kernel. Similarly, your definition of Fourier transform, e raised to I integration from minus infinity to infinity, e I omega t f t. That e I omega t, okay, that you are considering as a kernel. Okay, so it is that kernel definition in the integral transform is different from your kernel definition in your algebra.
Okay. Thank you so much, sir. Thank you.
Thank you, ma'am. Thank you.
Hello, sir.
Hello,
I have
Ali,
question.
sir. Ali, sir, please.
Yes. First, thank you for your nice presentation, sir.
Thank you, sir.
There are many different definitions of the fractional derivative. My question is, what is the advantage of using the Hilbert fractional derivative over other fractional derivative?
Hilbert derivative, only Hilbert derivative, na, sir? Okay, so Hilbert derivative is the derivative having the two parameter alpha and beta. Okay.
Yes.
So beta is we are taking varying in closed interval 0 to 1. Okay. Here is okay. So I think I have stopped my sharing. Okay. So here. This is your definition of Hilbert derivative. Okay, this definition incorporates these two definitions, sir. So it is not necessary to study two theory separately, Riemann-Liouville fractional derivative and Caputo fractional derivative separately. Okay, if you are studying the theory for this derivative, it includes the theory for Riemann-Liouville derivative as well as Caputo derivative. Okay, of course, we have to give a special attention toward the restriction on the function and all that, so that it must incorporate the theory of Riemann-Liouville derivative also as well as Caputo derivative also.
Thank you. Thank you very much.
Yes, sir. Yeah.
Excuse me, sir. So myself K. Muthuselvan from Tamil Nadu, sir.
Yes, sir.
Your presentations were very interesting, sir.
Thank you, sir.
I admire your work for the extensions of comma functions, the extensions of K cycles, sir. But I have one doubt about this type of extensions, sir. If I extend, can I extend the function from the R power half dimensional to half dimensional? It is possible, sir.
Sir, that in that direction I have not said. I think that will be concept of fractional derivative related to your multivariable. Okay, so in that direction I have not thought, sir. Up to now, I have not thought.
Okay, thank you, sir. But another I have one doubt, sir. If a lot of definition we put in the function, it should be absolutely continuously differentiable. What is the necessary to that differ that types of functions, sir?
Okay, so you can see that, sir, almost all fractional derivatives are defined in the form of integration. Okay, so whatever the condition is required for the existence of integration, that condition must be on that function, sir.
Okay. Thank you very much, sir.
Main point is what existence of fractional integral. Okay, so whatever the condition is required for the fractional integral, that condition is supposed for your fractional derivative. So in generally, I am talking, sir.
Okay. Thank you, sir. Thank you very much.
Sir, I think one question is there in the chat box, raised by one of the participants, Revati. So what happens for higher dimension, like 2D?
So just the same question of someone
I
asked in another direction only. Okay.
Yes,
so
yes,
I have not thought in that direction, sir. In multidimensional, I have not thought in that direction, sir.
Okay, sir. So and one more question. So when you say that approximation converges, so we mentioned that convergence in certain weighted spaces, right? C1 alpha, 1 minus alpha. So whether that convergence only in that particular space, or
Yes, sir,
depending upon certain the conditions available in the equation?
No, sir.
If,
no,
for example, you mentioned F belongs to C1 minus alpha gamma. When you take
yes.
So
That
whether it is
condition
related to that extra condition or always it is there.
Sir, generally, if you are considering any kind of differential equation, suppose your ordinary differential equations you are supposing, say y dash t is equal to f t yt. Okay, what space we are considering, sir? Space of continuous functions we are considering.
Yes.
Okay. For Caputo, we are considering a space of continuous function or a space of n-time differentiable function when alpha is between n-1 to n. Similar type of space we have to define when we are considering fractional differential equation, considering your Riemann-Liouville derivative. Okay. So, and as already I have discussed that we are considering generalized operators. So that space which we are considering for the solution, that must be generalized also. Okay. So in that sense, that space is defined. Okay. And you know that when we are considering the convergence in any metric space, okay, generally it is the space we have considered that is related with your weighted norm, and every norm linear space is again metric space. Okay, so suppose X is my metric. Okay, so convergence, divergence, that concepts are related with what your distance. Okay, and when we change the distance, your convergence and divergence concepts also change, sir. Okay. In that sense, our convergence we have considered only in that norm, sir, with particular type of that norm missed with particular type of that distance we have considered, sir.
Okay, sir. Thank you.
Okay,
So,
sir.
any other questions from the audience?
Sir, one more question as a concern, just I'm asking.
Please,
for
Birazar sir. Birazar sir,
for
please.
my own clearance, sir.
Yes, sir.
So
Yes,
as you said that this is a general representation for all the all sorts of fractional operators, correct? But while moving towards the generalizations, are we may miss some of the applications?
yes, surely, sir.
Physical phenomena.
Since your derivative is the concept related to derivative of the function with respect to another function, okay, that's why we cannot give directly physical interpretation of it. If you are assigning the particular value of the function psi, then it will reduce it to some particular type of derivative. Okay, suppose if I am taking beta is equal to 1, psi t is equal to t, then it will reduce it to Caputo derivative, and I can interpret the thing in the form of Caputo. Okay, if I am taking psi t is equal to t and beta is equal to say 0, it will be reduced in the form of what your Riemann level derivative, and I can interpret my things in the form of Riemann level derivative. So we cannot give directly interpretation in the form of Psi-Hilbert derivative. Physical interpretation we cannot give in the form of Psi-Hilbert derivative. Just like the case of Riemann-Stieltjes integration. We can give the geometrical as well as physical meaning for the integration, usual integration of f of t dt a to b. Okay, we cannot give the integration geometrical meaning to what your integration of your with respect to another function, like that, sir. It is.
Yeah. In addition to that, just as on a discussion, whenever we are using as a diffusion equations or any parabolic equations, and once we'll convert it into parabolic equations, that time we are telling that as a physical interpretation, it may be a subdiffusion or a super diffusion concept. But if we can try to replace it by this generalization operator, so at that point of time we cannot say any kind of such a physical phenomena.
No, sir, we cannot say.
Right. But I found there are so many results which replaced by this operator and did so many works. That's why
we cannot expect a physical interpretation in the form of generalized functions as psi.
Yeah,
that is the main thing, sir. Okay, just we can incorporating all type of it is theoretical improvement. We can say theoretical improvement. We can say, sir.
Yeah. Yes.
Good question, sir.
Thank you so much, sir. Thank you.
Any other questions? Okay, so if there is no question, so let me thank the resource person for this talk, Professor Kishore Kuche, for giving this nice lecture on fractional derivative. Thank you
very much, sir. And I thank Bhalekar, sir, convener of this conference, for giving me opportunity to talk in this conference. I also thank Geji madam. Geji madam and Bhalekar sir, my indirect guide in this field. I am developing myself, looking toward these two legends, I can say. Thank you very much.
Thank you, sir.
Thank you, Dr. Barney Balan, for chairing this session. Discussion was also nice. Thank you, Gidzi madam, for pointing out so many important things. Thank you, Dr. Kuche, for this quite generalized things related talk. Now,
thank you very much, sir. Thank you very much.
So let us move to last talk in this conference. It is by the convener, that means by myself. So I invite Gade sir. Gade sir, Kuche sir, please.
So am I audible?
Sir, I have stopped my screen, sir. Thank you, sir. Thank you.
You are audible, sir.
Am I audible?
Yes, sir.
So next talk, I would like to welcome Dr. Sachin Bhalekar. I have known him since long, and we had one work long ago, basically through Professor Gaiji. And recently, we have been working together on few more problems. he is also a convener of this particular conference, which is running very successfully. Almost 100 participants are there. We all miss coffee and bag and food, which used to be prime indicators for success of the conference pre-pandemic. But this is a new normal, and it is taking up really well. I'm really happy to see that. Let me briefly give his introduction. Actually, looking at the audience, he needs no introduction for this audience. Nonetheless, he currently works as associate professor at the School of Mathematics and Statistics in University of Hyderabad. He has finished his master's in 2007 and PhD in 2011 with Professor Gaji in University of Pune. He has published more than 55 research papers with outstanding citation number with 2,686 citations, which is really amazing for his age. He has worked on 4 research projects in BHM, CSIR, UGC, ACRB. 2 students have finished PhD, 1 is working. He has also received few awards, namely Padma Shri, NS Venkateshan Gold Medal for Best PhD Thesis from University of Pune, and A. Mathai Research Excellence Award from Society for Special Functions and Their Applications in November 2018. This is the work on fractional maps, and many of you may find it interesting for the simple reason that there are many problems which are waiting, low-hanging fruits waiting to be picked up, you can say. So not much has been done in fractional maps compared to fractional differential equations. Will be interesting to a large section of audience. Thank you. Over to Professor Bhalekar.
Thank you, sir, for a nice introduction. I'm sharing screen. Is my screen visible? Yeah. So title of this talk is Stability and Dynamics of Complex Order Fractional Difference Equation. So this is important declaration. I frankly say that I'm new to this field. Professor Varsha Gidzi, then Professor Iva Kaslik, they did nice work in this field. This is project headed by chairperson Professor Prashantyam Gade, and there are few research articles, some are published and some are available as preprint. So this first paper deals with the stability and synchronization of fractional order maps. It is published in the journal Fractals in 2021. Second is recently published, where we discuss synchronization in coupled integer and fractional order maps. And third one, which is main topic of this talk, that is stability and dynamics of complex order fractional difference equations. Okay, so this is available as archive preprint. It is under revision. I think no need to give introduction about fractional derivatives. Okay, as we have seen, when we deal with fractional derivatives, then these are nothing but arbitrary order derivatives. Where order can be any non-integer. Usually we take non-integer order, which is a real number, but it is not necessary. It can be a complex number. It can be a function of t, that means time, alpha can be time dependent, or it can be distributed order derivative. Okay, order can be distributed over some interval and so on. Okay, so many such generalized things are studied in this subject. On the other hand, I mean, when we consider continuous time things, then derivative appears. In general, we cannot have continuous time. There are so many natural systems where time is not continuous. For example, in population dynamics, usually time is discrete, where the difference equations appear. Okay, such equations are called as sequences or maps or discrete dynamical systems. Okay. And these are having applications in so many areas. So what we are going to discuss in this talk, we define the difference equation of fractional order, where fractional order is a complex number. Then we are going to study the stability of linear systems. We will give stability conditions for linear systems, and then study non-linear difference equations of complex order and investigate their dynamics. Let me give some basic things about the stability. I'm sharing another screen. Yeah, so first very basic thing is stability of system of ordinary differential equations. We consider system of this form x dot of t, or rather I just write x dot, x is function of time t, x dot equal to ax, where a is n by n real matrix. Okay. And this capital X is column vector in Rn. Okay, so it is from R to Rn, or we may take some interval as a domain of this function. It is state variable. Okay, so here the zero stability result is the zero solution of this system 1 is asymptotically stable. So actually, what is meant by asymptotically stable? Asymptotically stable means if we consider initial condition sufficiently close to origin, then and we evolve the solution from that initial condition, and as t tends to infinity, if that solution tends to origin, then we say that it is asymptotically stable thing. In other words, we can say that nearby starting solutions starting in the neighborhood of origin will converge to origin. Okay, so there are different concepts of stability in dynamical systems. So is asymptotically stable if condition is given in terms of eigenvalues of matrix A. If a real part of lambda is negative for all eigenvalues lambda of matrix A. Okay. In other words, we can say that real part negative means absolute value of argument of lambda is greater than pi by 2. Okay, so here stable region looks like this one. Let me sketch the stable region in complex plane. Okay, these are x and y axis in complex plane. So the left side part of this plane is stable region. So this is origin. And this is stable region. Now let us move to fractional order system. Similar thing. So second thing is consider fractional order system. Okay, instead of this x dot, where x dot is differentiation with respect to t, it is first order derivative, d by dt. Here we replace it by fractional derivative. Usually I'm taking Caputo fractional derivative. Okay, so this is Caputo fractional derivative d alpha x equal to f of x. Of course, f should I'm considering linear things first. So right hand side is same, capital A times x, A and x are same as here. So here this stability is discussed in yesterday's lecture by Professor Eva, and she has a nice paper which is generalization to such result by Matignon. Okay, so the result is that the zero solution of this system 2 is asymptotically stable if absolute value of argument of eigenvalues lambda of matrix A, this value is greater than alpha 5 by 2. Okay, so there is introduction of alpha here. Okay, so earlier we were taking alpha equal to 1, so this here we are having alpha 5 by 2. So how this stability region will look like? Okay, let us see. Here the angle should be greater than alpha 5 by 2. So this angle is okay. I'm taking alpha between 0 and 1. Sorry, I should explain here that alpha is a real number between 0 and 1. Okay, we may take alpha equal to 1. Okay, so and of course this angle is minus alpha pi by 2, and we are taking absolute value of argument. So whether it is alpha or minus alpha, that doesn't matter. And now stable region is all the part which is left hand side of this. I mean, okay, so all this is stable region. Okay, so what you can observe is this fractional order systems are more stable in this sense. You must have heard this sentence, ki fractional order systems are usually more stable than integer order. Okay, meaning is this one. I mean, stable region of integer order systems is subset. Okay, so this is stable region of integer order or classical systems, and this is quite larger, it is subset. Okay. Next thing I want to discuss is third point about discrete dynamical systems. So earlier our T was continuous. Okay, so here X was domain of this state variable was real line or some interval. So time was continuous. Okay, so these systems are also called as continuous time systems. Okay. And second part is discrete time systems. Or maps or discrete dynamical systems. Okay, so classical case. Classical means we can say integer order. Okay, so we have equations of the form, say xn plus 1 equal to axn if it is linear. Okay, and x0 is given here. N is time variable, it is discrete, n equal to 0, 1, 2, and so on. Okay, so if we know x0, we can find x1 and so on. So what is stability condition here? Here you can easily see that the solution is, or we can say general solution is xn equal to a raised to n into x0. x0 is initial condition. Okay, so in earlier case, this solution was in terms of exponential of matrix. Okay, here in this case, solution was x of t equal to e raised to at into some column vector, initial vector we can say, or in fractional order case, the solution was in terms of Mittag-Leffler function, and it was e alpha a t raised to alpha. This is matrix variant Mittag-Leffler function. So it is well discussed in the papers by Gidzi madam's first student Azizullah, Baba Khani, and Gidzi ma'am. Okay, so into, of course, column vector x0. There are nice properties of this function. Okay. Anyways, so here solution is like this, and we know that key this will tend to 0. Okay, so limit as n tends to infinity, a raised to n, it will be 0 if absolute value of a is less than 1, and otherwise it will be plus or minus infinity. Okay, depending on if a is positive, it will be plus infinity, otherwise it will oscillate. I should not say like this. I can say that limit does not exist. Okay, in other case, if a is positive, then it will go to infinity, otherwise it will oscillate. Anyway, so here stability condition is, so xn tends to 0 if absolute value of a is less than 1. So this is one dimensional thing. A is real number. Now if we consider general thing, higher dimensional thing, we can say higher dimensional thing is x n plus 1 equal to a xn, where a is, now I should say, m by m matrix, real matrix. Okay, so here we can say that a 0 solution is asymptotically stable if absolute value of eigenvalue of a is less than 1. It should be true for all eigenvalues of matrix A. Okay, so earlier we were having condition like this. Okay, now condition is this one. So how it the stability region will look like? Okay, so stable region, I'm sketching stable region, is very clear that it is circle in complex plane. So what is boundary of this stable region? It is mod lambda equal to 1, and mod lambda equal to 1 is unit circle. Okay, unit circle in complex plane. Okay, so actually my figure is not symmetric, so remember that I'm trying to sketch circle centered at origin and radius 1. Okay, though it does not look like. Okay, so inside this circle, it is stable region. Okay, so this is stable region for discrete time dynamical system. Okay, now what how to, important question is how to generalize these things to fractional order. I mean, it is very clear when we consider differential equation, how to generalize integer order differential equation to fractional order. So what we are doing here, it is nothing but dy dt. Left hand side is nothing but dy dt of x, and it is nothing but derivative of order 1 of state x. And what we are doing, we are replacing this 1 by a number alpha which is between 0 and 1. Now here we don't have such thing. Our system is of this form: xn plus 1 equal to axn, or like this. So how to generalize it, how to include fractional order? Okay, I was quite wondering when I was not aware of these things, and Gade sir talked to me regarding stability of such things. So I was unable to realize the things. I mean, where to introduce fractional order alpha. Okay, so what is motivation? So things are like this. So next thing is motivation in generalizing the things. Okay, so our question is how to generalize this discrete dynamical system to fractional order system. So how to get fractional order counterpart of this system? Okay, it is also very interesting thing. So what to do? We consider this equation xn plus 1 equal to axn. So I am rewriting this equation as, so I should give some number, maybe this is number 3. The system I consider is number 3. Okay, and this one 4. So rewriting 3, we get so how I'm rewriting this? I'm rewriting like this: xn plus 1, I'm subtracting xn from both sides. Right hand side is axn minus xn. Okay, now left hand side is quite familiar to me. Left hand side is in the numerical analysis, I came across the operator forward difference operator. Okay, so I know this delta u of x, or I should say delta u of t. Delta of u of t is u of t plus h minus u of t divided by h. Okay, so this is forward difference operator. If I set h equal to 1 and take t natural number and write u of t as u suffix t, I mean it will be u of 1, u of t. It is identified as u sub 1, u sub 2, etc. Then I can write this delta u sub t equal to u sub t plus 1 minus u sub t. Okay, h is 1. So I can identify left hand side with delta operator, and what we have left hand side as delta x suffix n, and right hand side is a minus 1 xn. Okay, so I'm able to write here in terms of difference operator, and I'm writing here delta raised to 1, because in the numerical analysis I'm having delta square operator also. It is nothing but delta composed with delta. Okay, so delta square u of t is delta of u of t. So easily we can have delta square, delta cube, etc. Okay. Now we are able to generalize the things because I'm having 1 here as in my earlier case. Okay, here I was having d1x and now and I replaced 1 by alpha, the number which is between 0 and 1. So I'm ready to generalize. Okay, so this was very important step. So generalization to fractional order map. So it will be delta raised to alpha xn equal to a minus 1 xn, and here we take 0 less than alpha less than 1. Okay, so this is a nice generalization, and now we have to get the definition of this operator. Okay, as in earlier case, there was gamma function in the definition of fractional order derivative. Okay, so similarly here we have okay, so I will discuss one more thing and then move to my lecture. Okay, I'm again doing another thing which is also important. So how to deal with nonlinear systems. Okay, I will explain what is delta raised to alpha, what will be stable region for this system. Okay, in all other cases we studied stable region. I will explain what is stable region. Before that, I want to explain the nonlinear systems. Okay, how to deal with nonlinear system. Okay. So we consider x dot of t equal to f of x of t. Earlier we were having x dot equal to ax. Here matrix A is replaced by function f. Here I am taking f to be continuously differentiable function on Rn. Okay, so f from Rn to Rn is C1 function, means it is differentiable, and derivative df or f dash is also continuous in that space. Okay, so here how to deal with this system. Okay, when we have nonlinear things, what we do, we discuss the local behavior. Okay, and locally things are very simple, linear. We know that whatever the curve may be, if we take a point on that curve and consider the neighborhood of this point, then you will realize that the neighborhood of this point is straight line. It will look like straight line. Okay, so this is nothing but local linearization of this curve, and such thing is used in so many branches of mathematics as well as applied sciences. So what we do here, first thing, we identify certain points. These are called as equilibrium points. So what are equilibrium points? Equilibrium points are nothing but steady state solutions, the solutions which doesn't depend on time. These are constant for all the time. Okay, so steady state solutions are called equilibrium solutions, and since these are points, we call them as equilibrium points, and we denote by x star. And of course, if x star is equilibrium point, it will be constant throughout. Okay, for all t. So its derivative will be 0, and if we substitute here, it should satisfy this equation. Means left hand side should be 0 or origin we can say, and right hand side should be f of x star. Okay, so this is the equation which can be used to find equilibrium points. Okay, so this is system of equations which we have to solve, and such points satisfying this equation are called as equilibrium points. Okay, so there are nice things in the neighborhood of equilibrium points. Okay, so I'm not writing the things, but I'm explaining. If and these are not rigorous definitions, remember, because there is time limit. Okay, so X star equilibrium point is called as stable if nearby solution starting in the neighborhood of X star stay nearby. That means nearby starting solutions stay nearby. It is called as asymptotically stable if nearby starting solutions converge to X star, and it is called as unstable if the things are not stable. That means nearby starting solutions, at least one nearby starting solution will go away. Okay. Anyways, so what we do, how to analyze this system, we linearize this non-linear system locally in the neighborhood of X star. Okay, so linearization in the neighborhood of X star. So we use first order Taylor's approximation, and it is not difficult to check that linearized system is x dot equal to ax, where A is Jacobian matrix of this function f evaluated at x star, derivative of f at x star. Okay, and then rest of the things are same as this one, that is linear case. Okay, so real part of eigenvalue, negative, etc. will come in picture. Similarly, for fractional order case, we do the same thing. We linearize in the neighborhood of equilibrium, and instead of A, we will have Jacobian. Okay. For discrete system also, we will have xn plus 1 equal to f of xn, and then we linearize in the neighborhood of equilibrium point. For difference equation, the equilibrium point is nothing but fixed point of f. Okay, so if we consider xn plus 1 equal to f of xn as a discrete system, and if x star is equilibrium solution, that means it is constant throughout, I mean for all n, then our left hand side is also x star and right hand side is f of. I'm muting you, Ahmad, because you are disturbing me. So in earlier case, I mean differential equation case, the equilibrium points were zeros of function f. Here the equilibrium points are fixed points of function f. Okay, I think this much introduction is sufficient. It seems quite lengthy introduction. Anyways, so now yeah, I'm sharing my presentation slide. So here we need, okay, so when we deal with differential equation, then Laplace transform is very important. I mean, when I want to find characteristic equation, so-called characteristic equation, okay, whose eigenvalues play important role in stability. Okay, so Laplace transform is important, whether it is integer order differential equation or fractional order, we need Laplace transform. On the other hand, if we consider discrete systems, then this Z transform is very important. So we are having a sequence Yn. Here we take sequence of complex function. Okay, no harm. So its Z transform is a complex function denoted by capital Y of Z. It is also denoted by Z of Y of Z, and it is a set. This series is convergent, absolutely. Okay. Now here we generalize the set of natural numbers to hn suffix a. This set here we take h to be positive, a to be real number, and we define this set to be a plus h, a plus 2h, and so on. And now we take a function x whose domain is this discrete set h n sub a. and values are complex number. So here we define forward H difference operator. Okay, earlier we were having, okay, this is same as the difference operator I discussed, except the thing that this function is complex valued. Okay, so it is x of t plus h minus x of t divided by h. Now throughout this presentation we take a to be 0 and h to be 1. Okay, so for general things there are nice papers. Okay, so for simplicity I am taking a equal to 0 and h to be 1. So here is operator, it is called as delta raised to minus alpha. Okay, when we are having d raised to minus alpha, we call it as fractional integral, and when it is d raised to alpha, it is fractional derivative. Similarly, here we are having two operators. One is sum operator and difference operator. Okay, sum operator is equivalent to fractional integral thing. Okay, so here delta raised to minus alpha x of t, it is 1. Okay, note that here alpha is positive real number. Sorry, I should have written here alpha greater than 0. Okay, so it is not negative. So it is 1 upon gamma of alpha summation s equal to 0 to n. N means here it is. Okay, so when my t is of this form, alpha plus n, okay, some integer. Okay, so 1 upon gamma of alpha summation s equal to 0 to n gamma of alpha plus n minus s divided by gamma of n minus s plus 1 x of a plus sh. Okay, so those who are familiar with fractional integral, Riemann Liouville fractional integral, I mean, now all are, I'm assuming that all are familiar with fractional integral operator. So you can see the analogy. Okay, so instead of integral, we are having summation, and there is similar kernel type of thing. Okay, and this function. Okay, so you can see similarities in discrete systems and continuous systems. Okay. Next thing is to define derivative of order mu. Mu is positive real number. Okay, I am again taking real numbers. It is between two integers m minus 1 and m. M is ceiling function of mu, means if mu is 4.5, my m will be 5. Okay, so the number integer which is bigger than or equal to that mu. Then muth order fractional Kaput-Leit difference is defined as delta raised to mu x of t is delta raised to minus m minus mu. Okay, so this is integral order. This is summation operator, and this is usual difference operator. M is integer, na? So this is usual difference operator. Delta raised to m, it is delta of delta raised to m minus 1 x of t, etc. Okay, fine. Okay, now again I will go back to the stable region. Okay, so this should be my equation. Delta raised to alpha x of t equal to a minus 1 x of t or x suffix t, that doesn't matter. Whether it is n or t doesn't matter. I'm taking discrete things. Okay, so please understand that here t is not continuous, t is discrete. 0 less than alpha less than 1. Okay, or you may consider this equation, this one. Okay, delta raised to alpha xn equal to a minus 1 into xn. So what will be its stable region? I will not discuss the detail. I will show you the stable region. I'm sharing Mathematica file. I hope it is visible. Okay, so here you can see one circle centered at origin and radius 1. This is stable region of integer order, and it is corresponding to alpha equal to 1. Okay.
and then I'm changing alpha from 1 to 0. Okay, so for this curve, alpha is 1, then I will take alpha to be 0.8, 0.6, 0.4, 0.2. Okay, so these different regions we can get. These are cardioid-like regions. Okay, and here you can see that this is not analogous with differential equation. For differential equation case, the stable region of fractional differential equation was superset of that of integer order differential equation. Okay, so for difference equation, it is not superset. Okay, it is different set. But what we are doing, for example, we are picking this point and pushing this circle from left side, and we are getting cardioid like structure. Okay, so these are the stable regions. So if our number A is in this region, earlier the condition was mod of A less than 1, or absolute value of eigenvalue is less than 1 for all eigenvalues of coefficient matrix. Here our condition is absolute value of eigenvalues of matrix A should belong to this region corresponding to that alpha. Okay, so here is the difference between the stable regions. Okay, so this is all about literature. Now what we did, we considered, okay, I think here we generalize, first we consider the generalized binomial coefficient. I mean, it is not difficult to see this. This is defined by Newton, and it is working for complex numbers. Okay, so we define this operator phi alpha tilde, which is this binomial coefficient n plus alpha minus 1. Here alpha is complex number u plus iv, it is in C, u positive. Choose n, it is well-known identity, it is minus 1 raised to n minus alpha, choose n. So yeah, next thing is convolution of this operator with x. So phi alpha tilde star x of n is summation is equal to 0 to n phi alpha tilde of n minus s x of s. Okay, so this is convolution while we take z transforms. Okay, therefore delta raised to minus alpha x of n is phi alpha tilde star x of n. Okay, so here delta means I'm taking complex number. Okay, here is generalization. Okay, I'm taking alpha to be u plus iv. I'm taking a real part of this fractional order, complex order alpha to be positive. Okay, and then I'm generalizing the earlier definition. Okay, so here my gamma function is okay with complex numbers. Okay, I'm replacing real number by complex, real alpha by complex alpha, and I'm taking real part to be positive. And z transform of this delta raised to minus alpha x of n is nothing but by convolution theorem, it is z transform of phi alpha tilde and z transform of x of n, and it is 1 minus z inverse raised to minus alpha x of z. Okay, so details are available in any book on integral transforms. Okay, so this is important result. Okay, I'm using. Now we consider delta raised to alpha x of t equal to a minus I. A is n by n matrix, I is n by n identity matrix x of t plus alpha minus 1. And here alpha is complex number with real part between 0 and 1. Okay, I'm restricted with real part between 0 and 1. Okay, of course there will be restrictions on imaginary parts that I will talk. So equivalent integral equation from literature is x of t equal to x0 plus 1 upon gamma of alpha. Okay, it is not integral equation, it is equivalent, I should say, equation containing summation operator. Okay, summation s equal to 1 to alpha 1 plus alpha to t plus alpha gamma of t minus s a minus I x of s plus alpha minus 1 divided by gamma of t minus s minus alpha plus 1. Okay, so by some transformations I can convert this to this equation x of t plus 1 equal to x0 plus a minus I phi alpha tilde star x of t. And now I'm ready to apply Z transform. Okay, and Z transform readily provide me this equation z into 1 minus z inverse raised to alpha into identity matrix minus a minus I x of z equal to this thing into initial condition x0 where mod z greater than 1. I mean, as per the condition of existence of Z transform, that means that series should be convergent. We can solve this equation if the matrix left hand side, this should be invertible. Okay, and this is invertible means determinant non-zero, and this is only possible when we take mod Z greater than 1. Okay, now from this, the characteristic equation is determinant of this left hand side z into 1 minus z inverse raised to alpha I minus a minus I equal to 0, and this stability condition is the zero solution of this equation 8 or 9, both are equivalent, is asymptotically stable. I should say locally asymptotically stable if and only if all the roots of determinant z into 1 minus z inverse raised to alpha I minus a minus I equal to 0 satisfy mod z less than 1. Okay, so for difference equation, if we get characteristic equation, the condition should be like this, mod z less than 1. Okay, now it is not easy to check such conditions, so we further simplify. So we will sketch the stable region. Okay, so when alpha is a real number between 0 and 1, these are the stable regions. Now I am dealing with complex alpha, so what will be my stable region? Okay, so it was our task. Okay, so we simplified this. I mean, for stable thing, z should satisfy this mod z less than 1. So on the boundary, mod z should be equal to 1, and mod z equal to 1 means z, complex number z, should take this form e raised to it. Okay, and t we take between 0 and 2 pi so that we get complete circle. Okay, so we here if lambda is eigenvalue of matrix A, then this thing is, without loss we can write this z into 1 minus z inverse raised to alpha minus lambda minus 1 equal to 0 as a characteristic equation. Okay, and lambda is any eigenvalue of matrix A. So here I'm replacing z by e raised to it. Okay, and alpha is my u plus iv. Okay, so here things are like this, lambda equal to 2 raised to alpha. Okay, after simplification there are quite tedious computations. Okay, so sin t by 2 raised to alpha into e raised to I alpha phi by 2 plus t into 1 minus alpha by 2 plus 1. Okay, and the parametric representation of boundary curve is this one, real part of this plus 1 comma imaginary part of this curve. Okay, so condition is if all the eigenvalues of matrix A lie inside this simple closed curve gamma of t, then the system will be asymptotically stable. Okay, so this is boundary of stable region, so our eigenvalues should be inside the stable region. Okay, so what we observed is if we sketch this region, then for certain values of alpha there are self intersections, and if there is self intersection, then that curve will not be simple curve, it is called as multiple curve. Okay, if this boundary curve is multiple curve, then we observe that all the solutions are unstable. If the boundary curve is simple curve, then the condition is like this. I mean, all the eigenvalues should be inside that region, then we get stable things. Okay, so further we were able to find the condition for the self intersection. Usually this thing is not simple to compute. I mean, finding such condition for self intersection is not usually simple. Fortunately we were able to do this. Okay, so condition is like this, Okay, recall that U is real part of alpha and V is imaginary part of alpha. Alpha is complex order of our difference operator. Okay, so condition is this one. We are of course taking real part between 0 and 1, and imaginary part should be between 0 and square root 2u minus u square. Okay, if this condition is satisfied, then this boundary curve of stable region is simple curve, and we get required thing, I mean stable region. So what we do, we take this thing 2 raised to alpha sine etc. Okay, we call it as beta of t. I mean it is nothing but this one, sorry, e raised to I mean replacing z by e raised to it, we are getting this one. I'm removing that one, I mean shifting just. Okay, so for simplification I'm writing it as beta of t. Okay, so there is self intersection or cusp like thing in this parametric curve. If and only if there are two distinct points T1 and T2 in this interval 0 to 2 pi, such that beta of T1 equal to beta of T2. Okay, I'm sketching the curve. Okay, so this, if this is beta of t and I'm saying that there is self intersection, this point, okay, this point is self intersection, then this is parametric curve. Okay, t is between 0 to 2 pi, so there should be two distinct values of t, say t1 and t2, such that beta of t1 is same as beta of t2. Okay, so this should occur. It is equivalent to this thing. Okay, I mean I'm using alpha equal to u plus iv, simplifying this, taking a real part, imaginary part, separating and equating like this. So I'm getting this tedious expression, and it look like v into log of sine of t1 by 2 plus t1 into 1 minus u by 2 equal to v into log of sine t2 by 2 plus t2 into 1 minus u by 2 plus 2k pi. This is angle argument, and this is absolute value, that is sine t1 by 2 raised to u e raised to v t1 by 2 e raised to I, sorry, it is earlier case, I haven't written absolute value. Okay, so there is one missing step, but original equation is this one, sine t1 by 2 raised to u e raised to v t1 by 2 e raised to I v log sine t1 by 2 plus t1 into 1 minus u by 2, and right hand side is just instead of t1 there is t2. Okay, you can easily see that if these two complex numbers are same, then absolute value should be same, means sine t1 by 2 raised to u e raised to v t1 by 2, it should be same as sine t2 by 2 raised to u e raised to v t2 by 2. And about arguments are either same or we can add 2k pi, k is integer. Okay, so if two complex numbers are same, then I should get these two things. Okay, and my target is to eliminate t1 and t1 t2 and just get relation between u and v. Okay, and after some tedious computations, I was able to get this as v square by 2 equal to 1 minus u by 2 into u minus 2k pi. Okay, and this is nothing but v equal to square root 2 plus 4k pi u plus u square. Okay, now if k is equal to, okay, k is integer, positive or negative. Okay, if k is negative integer, then we get v to be non-real, but v is imaginary part of our order alpha, so it cannot be non-real thing. Okay, so it should be, in fact, v is imaginary part we are taking without loss, I mean v to be positive. Okay, so negative values will not work. Further, this v is minimum if we take k equal to 0. For other values, it will have higher values. Okay, and I want smaller values. So by putting k equal to 0, I am getting v equal to square root 2u minus u square. Or this is equivalent to u minus 1 bracket square plus v square equal to 1. Okay, so this is boundary and our condition should be 0 less than...
Sachin.
Sorry. Yes. Yes. Yes, sir.
Yeah, so you have to look at time. Please, you may show few boundaries. You may show few boundaries for few values, and we don't have time.
Running over time. I think it is okay. Sorry. So yeah, I'm winding my lecture. Okay, so this is condition, and this is the region where horizontal axis is a real part of fractional order, vertical is imaginary part. Okay, so we tried different examples. So for example, first we take alpha equal to e raised to I pi by 4. That is nothing but 0.7071 into 1 plus I. The stable region for this alpha is sketched in figure 2. So this is figure 2. Okay, so from this to this one. Okay, when we take complex, then we are getting this one. Okay, so if we take our right hand side at 0.2 minus 0.5 I into x, this is my linear equation, this is the eigenvalue. So this 0.2 minus 0.5 I, it is inside this region, so I should get stable solution. And another value is 0.2 minus another value is 0.1 minus 2i, which is outside this region, and so I should get unstable. Okay, so for those values which are inside that stable region, I am getting stable solution. Outside I am getting unstable solution. These are oscillating things. Okay. We also consider nonlinear system here. Okay. I already have discussed this. So this is complex order logistic map where function is f of x equal to lambda x into 1 minus x. We have considered this system, okay, where alpha is complex number, and we discussed stability of equilibrium points using linearization. Okay, and we were able to get those results. So this is stability region for logistic map, okay, of one of the equilibrium points, and it is consistent thing. Okay, so stable solutions, etc. Okay, so many interesting things are considered. So I refer the reader, the audience to our preprint, archive preprint. Okay, so it was nice experience to work with the complex order systems. So I'm thankful to serve for matrix grant and University of Hyderabad for providing me grant through Institute of Imminence. Okay, so thank you. I'm sharing this slide again, I mean, for those who are interested. Thank you, sir. Now session is over. Yes, got it, sir. Got it, sir. Please unmute.
Yes, questions, please.
Yeah, it was quite a nice presentation, Sachin.
Thank you very much, madam.
It's a kind of, it is a new kind of domain one can now pose many questions actually. So
We tried to cover, I mean, variety there in conference. So this was, I mean, there was going lecture discrete system.
So in the limit, does it converge to fractional order continuous systems usual differential equations?
What do you mean, madam? I mean, here our n is 1, 2, 3, etc. We are taking discrete. Not like that.
Yeah, no, this is not
because I mean, we need to take another set. I mean, h into n0. I mean, step size should be h, and in that case, but I haven't checked it. But literature is with that operator, so things are like h, 2h, 3h, etc. In fact, it is a plus h, a plus h, a plus 2h, and so on. So we need a 0 and h to be sufficiently small, so that we may get. But
maybe in the limit.
In unifying discrete and computer systems, I heard that there is thing like time scale which you need, but I am not aware of it.
And chaos and all these things.
Chaos, yes. Chaos can also be observed in fractional order maps, and there are certain examples. It will be there even with complex fractional order. We are working on it now. Yes, it can be observed.
Yeah, it has to be
There is a concept of conjugated different integrals, Dr.
Yes, you are right, sir.
Even that is also worth exploring. In fact, Dr. Machado had himself written a good article on that. So I think initially it was Adams and Lovero, they started with it, and they gave this theory of conjugated different integrals. So if you have say s to the power q, then you have s plus s to the power q bar also, so that the both real and imaginary come into picture, but then the weird behavior because of that I that gets removed. So even that is also worth exploring. Actually, I would say.
Thank you for suggestion. Please share me that so that I will.
Yeah, I think there are a couple of researchers from Iran who have got some good PID controllers, complex order PID controllers designed.
Yes, I have seen your papers also regarding complex order control.
I have one work with my MTech student there actually from Pune.
Yes.
Correct. And there is also some. Please carry on, Dr. Sachin.
Sachin, there was a question from Bashir. He has raised the hand. Please, sir.
Yes, please. Bashir. Please unmute Bashir.
Sir Bashir.
If it is not possible to unmute, you can put your question in chat box. It is better. You can write.
In the meanwhile, I have one. Okay. In fractional order in normal differential equations and
yes, sir.
Difference equations, a simple thing was that you have on the left side this stability region, and if you take exponential of that, modulus becoming 1, okay, it was simply one-to-one correspondence. You take exponential of what is on the left side, and you get this modulus. Now we were thinking actually initially when we were doing this fractional order difference equation, maybe the analog of exponential is a Mittag-Leffler function, and you take Mittag-Leffler function of that particular order, and the stability region of fractional difference equation and the fractional differential equations would map on each other a simple functional transformation, which did not happen. Okay, nor did it happen for the complex order equations. So this was a big kind of disappointment. I still don't see in the stability region of fractional difference equation and fractional differential equation if there is a simple functional relation. Secondly, what has worried me is that this is something which lot of progress recently. But if you look at this is all about fixed point. But if you look at periodic orbit, say 2 period, 3 period, 4 period, okay, then it is the stability is very, very simple. for difference equation, a prime x1 into a prime x2 into a prime x2 modulus of this particular product is less than 1. It does not work out to be so simple for fractional difference equation, even real fractional difference of real order. And it is very, very different, particularly something is 0, something is not 0, etc., etc. So things are look far more difficult, at least right now. And even the stability region for equilibrium point, okay, has a functional form and all that, but it will be nice if one can have a mapping between, as Madam said, how one can approach between fractional differential equation and fractional difference equation, which is some kind of mapping is available via exponential function in differential in integer order. I hope I am clear.
Yeah. You know, when you go to fractional domain, certain things carry forward and certain things become really very different. Like so many other things, like
Dear viewers,
exponential function doesn't have
hello.
zeros. Tag Leffler function has infinitely many zeros. So sometimes certain things carry over, certain things are drastically different.
The following files.
So it is a matter of investigation only. And it's good. I mean, you are entering into new area. Secondly, I just wanted to know, how about physics? Since you are a physicist, do you see any kind of applications of this? I mean, to you statistical mechanics or whatever. I mean, whatever work you have been collaborating in. I mean,
not really.
This is not really.
Not really.
So not much physics, only.
No, okay. It is okay. There are several systems which have this kind of T raised to minus alpha kernel. This memory kernel is there in many systems. So in that sense, yes. But specifically with respect to map, I really don't know. I mean, this T raised to minus alpha becoming working only at integer times, I have not come across. But this power law decay memory kernel is there in many physical systems, from magnetic resonance.
Hello, sir.
To whatever.
Hello, sir.
Yes.
Actually, is there any concept? We know that curvature and torsion in differential geometry. So if you use the fractional calculus there, is it possible that fractional curvature, fractional torsion, fractional regular curve, all these concepts? Is there any work?
Maybe, but I haven't thought about it. Okay, but we tried curvature of the solution curves of fractional order systems in one of the papers. I will share with you. But generalization to fractional order, that I don't think.
Okay, thank you, sir.
There is one question in chat box by Priyanka M. Is there any relation between the step size and stability in numerical simulations? Yes, possibly it will play a role in stable region. I mean, quantitatively, at least, if not qualitatively. Okay. Without loss, we have taken h equal to 1, step size to be 1.
Good afternoon, sir.
Yes.
I'm Priyanka. I'm asking the question.
Yes.
If I take a system of continuous system, if I changing the step size, the stability will change.
Yes, of course. Yes.
Behaves like chaotic.
Yes, exactly. I haven't studied in that way. I mean, what if I change h from 1? Okay. I don't think there will be qualitative change. But I haven't seen, so maybe I need to say.
I think stability should not change with respect to
I mean,
step size.
C is talking about like numerical stability, where maybe, isn't it?
Thank you, sir.
Sir, I have one doubt about it.
now it is around 3:45. So I think better to email your queries to me. Okay, all of you have my email ID. So if there are questions, surely email. Okay, we need to stop here. Yes, sir. Gadi sir, please.
So this is this talk went slightly on longer side because of elaborate introduction by Sachin on fractional difference equations and why we should care for that. And I think perhaps it was needed because not many people work in this field, and this is new, and there are umpteen number of problems which are waiting to be solved in this particular things, both numerical front as well as the analytical. So I again thank Sachin for a nice talk, and I will stop here. Thank you.
Thank you, sir. Next announcement is valedictory function. I need a small break, so we will be back in less than 5 minutes. Thank you.
भालेकर सर सेम लिंक वरती आपण जाणार आहोत. भालेकर सर, वी आर गोइंग ऑन द सेम लिंक ना फॉर द व्हॅलिडिटी फंक्शन. भालेकर सर, भालेकर सर.
I believe he will be back soon. Please wait.
Yes sir, yes sir. Thank you sir.
Yeah.
Yeah. Welcome back to this final last session of this two-day conference. In this valedictory session, Professor Eva Kaslik kindly agreed to be chief guest, and Professor Varsha Gidzi work as president. I invite our Dean Madam, Professor Radha, to give her welcome note. Radha Madam.
Thank you, Dr. Sachin. Yeah, it is a great pleasure. In fact, on behalf of the school and on my personal behalf, I would like to welcome you all to the valedictory function. It has been a novel experience for us to host this international conference with the speakers and participants from different time zones joining us online. Dr. Sachin Balekar worked very hard to make this conference a success, and I heartily congratulate him and the organizing committee members for conducting the conference very smoothly and successfully. I'm sure all of you enjoyed the conference and will continue to have a fruitful interaction with each other. I'm sure that this conference has motivated a lot of youngsters to study fractional calculus and pursue it as a research area. And this conference gave an opportunity for those working in the area to share their work and provided a scope to network with each other. I hope we can have one more sequel to this conference in our school offline when the normalcy is restored, so that all the speakers and participants can visit our beautiful campus. I'm sure that all our faculty and students will then make the best use of their visit by interacting with them. Thank you, Dr. Sachin. Thank you, Dr. Sachin.
Thank you, madam. Now, as a convener, I read the report of this conference. So, respected Professor Eva Kaslik, chief guest of this session, Professor Varsha Gidze madam, president of this session, Professor Radha, Dean, School of Mathematics and Statistics, University of Hyderabad, eminent speakers, chairpersons, all my senior colleagues, friends, and participants. I'm very happy to present my report on International Conference on Fractional Calculus 2022. The conference was organized with the financial support by Institute of Eminence grant of University of Hyderabad. The inaugural session was held on 18 January 2022. Professor Radha, Dean, School of Mathematics and Statistics, welcomed the President, Professor B.J. Rao, Honorable Vice Chancellor, University of Hyderabad, eminent speakers and participants. In his presidential address, Professor Rao pointed out that fractional calculus has immensely enriched biology in many complex dynamic systems such as diffusion, heat transfer, neural impulses, population dynamics, and so on. He assured that this conference will be useful not only for mathematicians but also non-mathematicians. Further, he welcomed the delegates and wished grand success for this event. Dr. Sachin Balekar, convener of this conference, gave his remarks on this conference. This inaugural session was concluded by Dr. Archana More by proposing vote of thanks. The first talk in this conference was delivered by Professor Varsha Gidze from Savitribai Phule, Pune University. She talked on the new perspectives of fractional order dynamical systems. The session was chaired by Professor Radha.
Professor Ram Jayam Sahadevan from University of Madras was second speaker to discuss the analytic methods to time fractional nonlinear partial differential equations. Dr. P. Muthukumar from Gandhigram Rural Institute chaired this session. In the post-lunch session, Professor Iva Kaslik from West University of Timișoara, Romania, provided the stability analysis of fractional order systems with Prabhakar derivatives under the chairmanship of Professor B. Sri Padmavati. The last talk of first day was by Professor Hussein Jafari from University of South Africa, which was chaired by Professor P. Balasubramanian. Professor Jafari elaborated the numerical study of fractional order population dynamics model. He also discussed various models involving pandemics. At the end of first day, there were 7 parallel paper presentation sessions chaired by Professor Deepak Paspate of Babasaheb Ambedkar Marathwada University, Aurangabad, Dr. Amit Prakash from NIT Kurukshetra, Dr. N. Annapurani from Bhartiyar University, Coimbatore, Dr. Mohan Jintamani, Dr. Nageshwar Rao, and Dr. Archana More from our school, University of Hyderabad. Around 62 researchers presented their work in these 7 parallel sessions. The second day of conference was started with the talk by Professor Vishwesh Vyavhar from RAIT Mumbai. He presented the FPGA implementation of special mathematical functions used in fractional calculus. Professor Subhash Kendre of Savitribai Phule Pune University chaired this session. Second talk of this day was by Professor Shantanu Sahare, National Institute of Technology, Rourkela, who explained the analytical and numerical methods in modeling a Riesz fractional reaction diffusion mechanics system and Riesz fractional nonlinear Schrodinger equation in quantum mechanics. Chair of this session was Dr. Dilip Kumar from University of Kerala. Professor Subir Das from Indian Institute of Technology, Banaras Hindu University, Varanasi, delivered third talk, which was chaired by Dr. Krunal Kachia, Charotar University of Science and Technology, Gujarat. The topic of his talk was two-dimensional fractional order nonlinear transport phenomena problems in porous media. In the afternoon session, Dr. Kishore Kutse from Shivaji University discussed the calculus of generalized Hilbert fractional derivatives, and Dr. Barani Balan from Central University of Tamil Nadu chaired his session. The last talk was by Dr. Sachin Malekar, University of Hyderabad, who discussed the stability and dynamics of complex order fractional difference equations. This session was chaired by Professor Prashant Gade from Rashtrasanta Tukadoji Maharaj University, Nagpur. As a team, we tried to cover various aspects of fractional calculus, including theory as well as applications. I'm very happy to see that there were nice discussions. Eminent speakers participated in the discussion, and I hope that the participants will surely get benefited of this conference. I'm thankful to all the eminent speakers, chairpersons, organizing team, participants, university officers, IOE office, and everyone for making this event successful. Thank you. Now, next thing in this session is feedback by participants of the conference. So I invite some participants like Anjali Sang. Are you there, Anjali Sang?
Good afternoon, everyone. Am I audible?
Yes, yes, please.
Thank you to Koji ma'am. I really, it's really very, I say, wonderful lecture by you on fractional calculus. Various concepts, they are very nicely explained by you. And many other persons, speakers, they also explain their research work very nicely. So it's really a very wonderful or informative platform for research scholars like us. So I'm very thankful to organizing committee, to University of Hyderabad for organizing such a wonderful conference for us. Thank you, everyone.
Thank you, Anjali. Next is Dr. Gunwant Birazdar from Tata Institute of Social Sciences. Are you there?
Yeah, dear all, a warm and very good evening to all mathematics lovers over here. First of all, I express my sincere thanks to School of Mathematics and Statistics, University of Hyderabad, and convener, coordinator, and all other colleagues who are involving this activity for serving such a full plate of delicious lunch of the fractional calculus. We came with small expectations, but we have received a lot during these conferences. I have observed the following points in the conference, which I wanted to cite over here. The overall conference is wonderful. All the resource persons in the conference are eminent and well versed in their areas. The number of participants in the conference within the country and outside the country are significant, which shows the gravity and success of the conference. Good numbers of paper were presented during the conference. The topics covered in the conference are very focused, precise, and to the points. If you can see the speakers like Gedji ma'am, which started the first lecture of this conference, which was very insightful, knowledgeable, and which motivates to the youngsters to work in this field. Not only this, the other resource persons like Professor Sadevan sirs, Professor Iwa, Hussein Jafari, Professor Vewari sirs, Professor Shantuni Ray sir, Professor Kuche sirs, and lastly the convener of this conference, Sachin Bhalekar sirs. They have provided a lot of insights in the fractional calculus, where some lay person or some lay research man or lay research scholar can easily start his and her work in different directions. This conference attempted to focus on different angles and different dimensions of the fractional calculus. Surely this will help to the all researchers who are working in these fields. I'm very much thankful to organizer for giving me this opportunity, and I'm very much thankful to all the eminent professors and leaders in these fields for providing this wonderful, fruitful discussions during this conference. Thank you so much, sir.
Thank you, Dr. Gunman. Next is Wahid Hussaini. Are you there, Wahid Hussaini? Wahid Hussaini? I think he is not there. Madhukar Dhanze.
Okay, thank you, sir. It gives me immense pleasure to share my views on these occasions. So today we are gathered here for validity functions. So the today's president, renowned academicians, Professor Varsha Gedji madam,
distinguished Professor Siva Kaslik from Romania, and dear participants, speakers, and organizing committee. In one word, I say the fantastic conference. Thanks so much for all of you, thoughtful and effective organizations. I'm really impressed with the commitment and efficiency of organizing committee. So I will say and explain this conference in some few parameters. Firstly, it was free without registration fee. And in this pandemic situation, so everyone got the opportunity to for paper presentations in online mode. All the sessions are started as per the schedule. All the speeches are very nice and informative, and overwhelming response of the participants. Because many times in first two sessions, yesterday I was on YouTube live, unable to enter the meet. So this overall, it is a very wonderful conference. I think first conference on fractional calculus I attended in University of Pune, organized by Professor Gezi Madam, and another at the superannuation time, and this is booster dose for me. So definitely this is very good for me, and overall it's very nice. Thanks very much organizing committee once again for this wonderful conference. Thank you very much.
Thank you, sir. Next is Yogeshwari Patel. Are you there, Yogeshwari?
Good evening, everyone. First of all, I would like to congratulate convener and organizing committee for organizing an excellent international conference on fractional calculus. As Radha Madam said, that this conference will motivate the youngster as well as researchers to work in this field. That purpose has been served because I am new in this field and now I am motivated that yes, I can do it. And I am having lot of information from this conference that will help me in my research work. Thank you for organizing such a wonderful conference and motivating researchers in this area.
Thank you, Yogeshwari. Azizul Islam, are you there? Any participant outside India, please, Mohammad Waid Raza Hussain. Would you like to express anything? Yeah, please.
Hello, everyone. Thank you very much for everything. And I get so many inspirations and motivation for writing. Especially, thank you very much for Professor Jafari for his speeches today, and Professor G. Thank you for everyone. And I hope next time I can join you, because we are working on a meshless method in the fractionals, and right now we are looking for an application fractionals in the Pers media, but we have so many restrictions for these ones. I can get so many idea for this conference. I hope next time we have some presentation, because right now we are working with Professor Jeffrey on the advection diffusion problem with the meshless, and some new area is coming from fractionals. It's like the neural networks, and I'm also, we are working on the pre-dynamic is kind of the meshless methods, but for finding the applications, we have a line distance. So basically, I'm working on the mechanics engineering, computational mechanics, and so many theoreticals. I can get some idea for proof the stability and the convergence for my problems, because a new methods need the proof just the numericals, some just present some numerical example is not enough. So I get still so many ideas to prove my problems. Thank you very much for everyone. I hope join you Till next time, thank you very much for Professor Jafari. Thank you very much for Professor Eva, and thank you for Professor Wisha. Thank you.
Thank you. Thank you. Professor Hussein Jafri from speakers. Would you like to say a few words? You may give suggestions.
Yeah, now I must say good morning to Prof. Eva at least, and also good evening to Dr. White in the China, and good afternoon to my friends in the India. I really appreciate you, and it was very interesting. And it is like a World Cup. It started by Prof. Daftar Dargeji and finished by you as a final, and it was very interesting, and I like your talk also, and I hope next time you give this presentation 1 hour more, then we learn a lot of things. And also Prof. Das and Prof. Eva and all talk was very interesting for me myself. Really, I learned a lot really. And thank you so much. And I'm really appreciate University of Hyderabad to give this opportunity. We attend from the all part of the world, and it is very interesting. Thank you so much. And I really appreciate my supervisor, Prof. Daftardar. She helped me a lot, and I learned a lot also from her talk yesterday. Thank you so much.
Thank you, sir. Any other speaker? Anyone of my colleagues from School of Mathematics? Suggestions or views?
All right.
Yes, thank you, sir.
Sachin, I had already expressed my opinion on writing. In any case, it's a wonderful conference. I could understand a bit, even though my area of research is completely different from all this. But still, I could make out certain things from these talks. Particularly, 2-3 talks were quite interesting to me. So, congratulations. And I hope in the normal times we will be having a nice offline conference here, and hope all the participants will get an opportunity to visit our place here and enjoy the mathematical events in the future. Okay, thank you.
Thank you, sir. Professor Shankar Narayanan worked in TIFR Mumbai. He is well-known number theorist, and now he is our colleague. Anyone else? Okay. We are moving to next thing, that is address by Chief Guest Professor Eva Kaslik. I request Professor Eva to share her views.
Thank you very much. Can you hear me?
Yes.
Everything okay?
Yes.
Okay, so thank you again, Dr. Balakar, for giving me the opportunity to participate at this extremely interesting international conference on fractional calculus. It has been an honor for me to be an invited speaker along with respected professors with remarkable results in the field, Professor Varsha Geji, Professor Sahadevan, Professor Jafari, Professor Vyavahare, Professor Saharey, Professor Subir Das, Dr. Kucha, and of course yourself, Dr. Balakar. Okay, so I would like to express my sincere thanks to the organizers for bringing together such an amazing community, not only the invited speakers and the presenters of many contributed talks, but also the large number of attendees, many of the young researchers, and also doctoral students. It is well known that the notion of fractional derivative first appeared in a letter from 1695 written by Guillaume L'Hôpital to Gottfried Leibniz, where the question was raised if the derivative of integer order could be extended to fractional values. Leibniz studied studied this problem for the power function, and in his reply letter to L'Hôpital, he mentioned it leads to a paradox from which one day useful consequences will be drawn. Around the same time, Leibniz also wrote a letter to one of the Bernoulli brothers describing the relationship between the binomial theorem, which is a well-known result of Leibniz, and the Leibniz rule for the fractional derivative of a product of two functions. Fractional calculus was introduced in one of Abel's early papers, which was published in Norwegian in 1823. Where we can find all the main elements: the idea of fractional order integration and differentiation, the mutually inverse relationship between these operators, the understanding that the fractional order differentiation and integration can be considered as the same generalized operation, and the unified notation for these operators of arbitrary real order. In an independent manner, the foundations of these subjects were laid by Liouville in a paper from 1832. And throughout the past centuries, many important scientists have had stronger connections to this field. And I would also like to mention Fourier, Euler, Lagrange, Laplace, Karl Weierstrass, Bernhard Riemann, Anton Grünwald, Alexei Letnikov, Oliver Heaviside, Magnus Mittag-Leffler, and Marcel Ries. The research area of fractional calculus has experienced a huge development during the past several decades, particularly in light of several important applications. Researchers in the applied sciences started to pay attention to fractional calculus and verified that it constitutes a formidable tool to describe many natural and artificial phenomena embedding long-range memory effects, which classical integer order calculus neglects. The first conference dedicated to fractional calculus was actually organized back in 1974 by Bertram Ross at the University of New Haven. The first monograph is due to Oldham and Spanier in the same year, 1974. While back in this year, there was only one book and one conference proceedings dedicated to fractional calculus, at present, there are more than 250 books on this topic, while the number of research articles have risen to many thousands. When it comes to research articles, they can mainly be classified into three categories: mathematical analysis, numerical methods, and applications to diverse fields such as physics, engineering, biology, economics, population dynamics. It is actually expected that in the years to come, this field of research will further experience an exponential growth, while many applications of fractional calculus and fractional dynamics are yet to be uncovered. The advance in the field during the past 2 decades has led to so many further open questions which are worthy of investigation, and hence I would like to encourage young researchers to pursue this field and advance knowledge. After 2 years of living in a world controlled by the pandemic, I believe that we have all learned to greatly appreciate online conferences, which are able to bring researchers closer without the barrier of long-distance travel. Although I would love to visit India one day, and of course the University of Hyderabad, I am thankful for the opportunities, and I am happy to be a part of some really rewarding international collaborations, which are sustainable thanks to the many online tools that we have at hand nowadays. Thank you again for the kind invitation, and I look forward to meeting you again online or in person, of course, as soon as possible. Thank you.
Thank you, Professor Eva. You are always welcome to University of Hyderabad. Now I invite Professor Varsha Gidze Madam for presidential talk.
Hello, everyone. It's really an honor to be here. I'm really thankful to the authorities of University, Hyderabad University, Professor Radha, Dean of School of Mathematics and Statistics, convener Dr. Sachin Bhalekar, and other hardworking members of the organizing committee. So it is, I feel like having a reunion with the my students, colleagues, collaborators, and it is really a very wonderful moment that we had, as somebody pointed out, that we in 2012 in Pune University, we organized first conference, and followed by second after 5 years. And in these two conferences, I edited 2 books and documented the presentations and research discussed there. Now, due to pandemic, actually our horizons are widened, I should say. Those who want to attend can attend free of cost without any borders. And really to the point, we can communicate. No time is lost in dinners and lunches and teas. And we are really covering. So it's amazing number. 66 papers are presented. And we really can talk with thanks to the advancement of technology. And this subject is grown quite to some height. So for the newcomers, it is really an area where they can embark upon very interesting projects, because it is now an established area. And so many, as Professor Eva Kaslik has pointed out, so many books and such literature is available, and people are now taking fractional calculus and its applications very seriously. Also, it is an interdisciplinary area. So right from engineering, bioengineering, economics, physics, and to mathematics, to very detailed pure mathematics. So depending upon whatever is your bent of mind, you can contribute to the topic. So it's the conference was really worth it. It is I think a lot of potential in Department of Statistics and Mathematics of Hyderabad University. So you have active, enthusiastic young faculty members who will take the lead. And now in India also we see almost uniformly now there are people distributed who are really seriously working and coming up with very important results. And very importantly, it is all leading to a very meaningful research, like say contributions from physics is used, contribution from engineering is coming, and then this is truly become multidisciplinary, and hence very useful kind of research is coming out of this. Because after all, with calculus 300 years we have developed so much. So fractional calculus, I should say, next 600 years it will give us more applications, more meaningful kind of results and formulations of various processes. So with that note, I thank again Professor Eva Kaslik. I always cite that analytical result, beautiful result in my talk, which motivated me to take this study of fractional order. So much of numerical work was there. So many results were there, but fractional order dynamical systems can't have closed orbits. I mean, it's interesting kind of analysis she could. So with the, so you make friends, you make collaborators, and such informal discussions really motivates us and compels us to peep into others work, others areas. And I think that is the way science grows and meaningful research comes out. So it was really very wonderful conference and very beneficial to all the faculties from engineering to pure mathematics, and covering such a wide range of topics. And definitely the organizing committee, the convener, and I also appreciate the support given by the Department of Statistics and Mathematics of Hyderabad University. It's really a wonderful, it is really a wonderful experience to see all the colleagues working wholeheartedly towards one goal of making the conference successful. So it's I really appreciate all this and hope in future this will be continued. This will be also some other faculty members will also take lead. Some other universities now, those who are speakers can also take a lead and arrange such things, at least virtually. And let us meet again and again and do more and more important research. Thank you.
Thank you, Madam, for encouragement. It is really a teamwork, and yes, it is true that the members of School of Mathematics and Statistics helped a lot. University also supported this conference, and then only I was able to do it. Even if it is online, we cannot do without support. My senior members, Professor Radha Madam, Padmavati Madam, they guided me, and my juniors team was there. Okay, so now last part, I invite coordinator of this conference, Dr. Abhay Soman, to propose vote of thanks.
Okay, thank you, Sachin. So it is my great pleasure to thank all involved here on behalf of the School of Mathematics and Statistics, University of Hyderabad. We would like to express our gratitude to Honorable Vice Chancellor, Professor Vijay Rao, for his support. We would like to thank Professor R. Radha, Dean of the School of Mathematics and Statistics, for her support and guidance. We are thankful to the Institute of Eminence, University of Hyderabad, for providing funding for this conference. We thank Professor Geji for presiding over a session. We also extend our gratitude to Professor Iva Kaslik for accepting our request to be the chief guest. We would like to thank all invited speakers, Professor Iva Kaslik, Professor Hosni Jafri, Professor Varsha Geji, Professor Ramajayam Sahadevan, Professor Santanu Sahare, Professor Subir Das, Professor Vishwesh Vagware, Dr. Kishore Kuche, Dr. Sachin Bhalekar for presenting their work. We thank chairpersons of the invited talk, Professor R. Radha, Dr. Muthu Kumar, Professor Padmavati, Professor Bala Subramaniam, Professor Subhash Kendre, Dr. Dilip Kumar, Dr. Krunal Kuchia, Dr. Barani Balan, and Professor Prashant Gade. We are also thankful to Professor Deepak Pachpate, Dr. Amit Prakash, Dr. Mohan Chintamani, Dr. Nageshwar Rao, Dr. Annapurani, Dr. Kishore Kuche, Dr. Archana More for chairing paper presentation sessions. We thank our office staff for all their help and assistance. Last but not the least, we thank all participants for their enthusiasm. We hope that the conference was very fruitful and the participants would continue discussions beyond the conference. Thank you.
Thank you, Dr. Abhay. Now, with the permission of President, I declare that the session is over. Vijayan.
Sorry, Sachin.
Yes, sir.
May I have one suggestion?
Yes, please, please.
Because all conference, we have a photo of the conference. So if no mic, people can switch on the camera and we take a picture.
Yes, sir. Please.
Yeah, that is a very good suggestion.
Please switch
we
on.
will take a screenshot. Everybody,
Yes.
please open their video.
It is not possible to cover everyone because of that screen limit, but whatever possible we can do. I'm taking snapshot. Yes, sir. Done. Thank you for suggestion.
Okay, this session is closed.
Okay.
Thank you one and thank you all.
Congratulations, Sachin.
Thank you.
Thank you, Radha.
Congratulations again from me.
Yeah.
Congratulations, sir. Congratulations.
Thank you.
Shall I close the meeting, Radha?
Thank you.
Thank you.
Thank you, Kaslikma. Miwa Kaslikma. Thank you. Bye bye.
Bye bye.
Speakers.
See you.
Bye.
Meet,
See you soon.
meet you sometime. Let us have.
Let's hope so. I hope so. Yes.
Let us
I
have a
hope so
conference
too.
in South Africa.
Yes.
Welcome. Most welcome.
Because things look better in South Africa at this point, I think, from the
Yes.
COVID point of view.
Yeah, because of COVID.
Actually, online it is better, I think. I mean,
For
It is
now, for
free
now.
of cost. That is the best part.
free of cost. Nice.
Thank you again.
Okay, meet you all
Stay
sometime.
safe.
Yeah, see you.
See you.
See you.